Good morning, everyone. Welcome to the Congress. We're going to be starting today. I have the pleasure to present to you Dr. Tom Strydom. He comes from South Africa. He's qualified as a veterinarian at the University of Pretoria's Onderstepoort in veterinary faculty in 1989. Started his career at a state of veterinarian in the eastern province of South Africa, joined private practice in the Western Cape for a while, returned to the Eastern Cape as a state veterinarian, and started with research mainly in parasitology at the SABS Veterinary Test Facility in East London in 1996. In 2002, joined the Intervet Melelane Research Unit as a site veterinarian and became the test facility manager of the research unit in 2008. Intervet became part of Merck as MSD Animal Health in 2011, and since 2015 became the technical director of parasiticides in the global ruminant business of MSD Animal Health. So we would like to welcome for the keynote lecture to Dr. Tom Strydom.
Good morning, ladies and gentlemen. Let me just see if this clicker is working. Mine is not working. I don't know if I pressed something wrong here. Before I start, I want to thank the World Buiatrics Congress for inviting me to give this lecture on the economic impact of parasites in beef animals or beef cattle. I also want to thank my co-authors on the manuscript that we published the last year, Kathy Heaney from Heaney Veterinary Consultants, and Bob Lavan and Siddhartha Torres from Merck Animal Health, who contributed a lot to the manuscript, and also Kathy and Bob that were instrumental in the, instrumental in the writing of the manuscript. But before I want to start, I just want to tell you a bit about how did the writing of this manuscript started. Before I joined MSD Animal Health, the global ruminant team approximately 9 years ago, I was involved in research and development for approximately 22 years. Started my career as a state veterinarian, said earlier, and eventually joined a contract research organization in South Africa where I did research and development work for the pharmaceutical companies on parasitology mainly. And those were for Pfizer Animal Health, Bayer Animal Health, Verbac, and a few other generic companies as well. And then later on, of course, I joined MSD Animal Health from 2002 till 2017. But at the same time, when I was doing my research or the research and development work on veterinary products for registration purposes, I also started doing research on parasite resistance, looking at parasite models and also visiting farms to advise farmers on parasite management. And what I've learned is the first thing was that farmers very seldomly follow science when they do parasite control. Farmers follow the advice from their fathers and their fellow farmers, which is a huge problem for us. And it's very difficult to change their minds. Also, the veterinary involvement from veterinarians itself was lacking, or is still lacking in many countries. Farmers will most of the time will actually follow the advice from sales reps from pharmaceutical companies. And I do understand why, because veterinary involvement, as one vet once said to me, is parasitology is not sexy enough for them. But I also learned that to motivate a farmer and to change his mind in changing his way of thinking in parasite management is a challenge. because they don't understand the production losses very often, what they're actually experiencing. And that is why I initiated the writing of this manuscript, to make a document that could be easier to understand and read for farmers so they can see what the impact of parasites may have on their productivity. We actually researched about more than 200 publications in writing the manuscript. So there's a lot of information, and a lot of it's very confusing sometimes. But let's look at the current situation. The global human population continues to grow at a rate of approximately 1% per year. And natural resources, farmland, is unchanged, and in some countries actually getting worse. Feeding an increasing population in a sustainable way is a challenge. And beef or meat consumption is an increasing source for many people worldwide. The demand is, and this is an estimate that was done in 2020, that over the next decade, the consumption of meat is expected to increase by 14%. That is compared to figures from 2018 to 2020. Beef production is only expected to grow by about 5.9% to supply a portion of this increasing demand of protein. There are many challenges to beef production, and parasitism is probably at the top of the list, although it's not always recognized like that. Parasites and parasite-borne diseases, they influence the marketing and trade of animals and food products. Parasite infestations reduce live weight, milk yield, feed efficiency. It increases liver condemnations. It increases mortalities, of course. It has a negative impact on reproduction and a negative impact on the immune response from animals, not only to natural infections, but also to the vaccines that we administer to them. To maintain profitability, we must implement measures to mitigate the effect that parasites have on the animals in a positive economic way. And to assist beef farmers and veterinarians, this paper aims to review current trends on the impact from the most economically significant parasite in beef cattle. When we did the research, we actually found that the parasites that has the most impact on beef cattle are gastrointestinal nematodes, respiratory nematodes, of course, there's only one, trematodes, and ticks. Not only from the diseases or the clinical symptoms that they cause from that perspective, but also because of resistance that these parasites have developed against current antiparasitic products. The ones, I'm going to list them there quickly. You can see them there. The first one, gastrointestinal nematodes, is the brown stomach worm, or Sartagia or Sartagi. The small stomach worms, the Trichostrongylus species. The small intestinal worms, Cuperia species. Nodular worm, Isophagostomus radiatum. The barber's pole worm, or wire worm as it's called, Haemonchus plasi, the long neck worm, Nematodaris evolutionis, and then cattle hook worm, Binostomum phlebotomum. And then there's the respiratory roundworm, Dictyochorus viviparus. The trematodes, of course, is the two fluke species, Fasciola hepatica and Fasciola gigantica, and the rumen fluke, Paramphistomidae. And then the tick species. The first one, top of the list, is the single-ose tick called tropical cattle tick or cattle fever tick, or in some countries even the blue tick, Rhipicephalus, Bauphilus microplus. And then there's a few multi-ose tick species, of which brown-eared tick, Rhipicephalus appendiculatus, particularly in Africa, and then 3 Amblyomma species, and then Exodus ricinus in Europe are very important. Now, as shown in that table, we can see that, as I said, roundworms, ticks, and trematodes have the most economically impact on cattle production, but it doesn't mean that there aren't any other parasites. Flies, lice, and mites also have economic impact, but not to the extent that these other species have. In addition to the direct effect that these parasites may have on the animals, they're also the vectors for bacterial, viral, and of course, protozoan diseases such as babesiosis, anaplasmosis, East Coast fever is a disease of Africa, or theileriosis in many other countries, and then heartwater rickettsial bacteria from cattle in Africa. If we look at the beef cattle parasitism and the economic impact it has, now the countries, the 6 countries that contributed to the highest proportion of beef in 2022 is the United States of America, Brazil, China, the European Union, Argentina, and Mexico. And they contributed to 74% of the estimated 58 million tons, metric tons of beef carcass weight in 2022. Now, if we look at that table, we will see that Brazil, the total economic losses from the cattle tick, Rhipicephalus microplus, gastrointestinal nematodes, flukes, flies, and also grubs, was approximately $14 billion losses experienced in 2022. In Mexico, the 6th largest producer from the 6 most important parasite species was approximately $1.4 billion. In Europe, only from gastrointestinal nematodes, the losses was 0.42 billion euro. And in Australia, in 2015, this is the latest figures we could get, due to the cattle tick again, Rhipicephalus microplus and gastrointestinal nematodes, was 0.25 billion Australian dollars. In the US, with approximately 45 million cattle, the losses due to gastrointestinal nematodes alone was about $8.5 billion. Those are the latest figures that we had. Now, in addition to the financial losses, of course, parasitism impacts also the health and welfare of animals. And the World Health Organization defines good animal welfare when an animal is healthy, comfortable, well-nourished, safe, not suffering from unpleasant states such as pain, fear, and distress, and is able to express behaviors that are important for its physical and mental state. And good welfare requires disease prevention and appropriate veterinary care, shelter, management, and nutrition. Low levels of gastrointestinal nematodes have been shown to negatively, of course, affect animals, their feeding, their rumination, their resting behavior, standing behavior, and therefore negatively impact their welfare. Tick infestations, apart from the diseases that they transmit, also have a direct effect on animals, causing irritation, inflammation, hypersensitivity, and dermatitis, and can also transmit paralysis toxins. Now, this is a very important one. As cattle and sheep infected with gastrointestinal nematodes are implicated or appear to contribute to greater greenhouse gas emissions, with some governments issuing emission reduction targets. Effective parasite control measures may become necessary to help satisfy increasing political and societal pressure. Therefore, losses from parasitism justifies the implementation of effective management. I rather prefer to call it management than control measures to the major parasites affecting beef cattle to protect the profits, to improve animal welfare, and perhaps play a role in reducing greenhouse gas emissions. Successful, cost-effective, and profitable management of parasitism is dependent on geographical areas and the types of parasites and the extent of the effects on animals. And measures to control them will differ by geography, climate, cattle genotype, age of cattle, production environment, management practices. For example, cattle genotypes differ in their susceptibility to various parasites. We know that Bos indicus breeds are more resistant to ticks than Bos taurus breeds. There are some studies that even indicate that Bos taurus breeds may be more resistant to gastrointestinal nematodes, but that could not be substantiated, and some studies even showed the opposite. Young cattle, particularly those on pastures for the first time, tend to have higher loads of gastrointestinal nematodes. Even individuals within the same breed, within the same herd, same cattle class and management system will have variable degrees of inherent resistance to nematodes and ticks. Cattle on pastures have greater exposure to nematodes and external parasites. And then, of course, seasonality and nutritional status will also have an effect on exposure and the response. The distribution of parasites, oftentimes the disease they transmit, is expanding, because compatible environmental conditions that support their life cycle are expanding. I always, when I talk to farmers, I ask them, how is it possible that ticks can move 1,000 kilometers while they actually only cover an area of approximately a meter by a meter? Because farmers are moving cattle from one side of the country to the other side. I say they put wheels under their feet. And that is ineffective biosecurity measures. Examples are broader distribution of the tropical cattle tick in West Africa, and then the recent discovery of the Asian longhorn tick, or bush tick, Hemiphasalus longicornis, in the United States. While climate is an important driver of tick and helminth distribution, husbandry practice also have an impact on the transmission to livestock. For example, pasture management with knowledge of local parasite epidemiology can successfully limit parasite exposure. Pasture rotation, annual or biannual renovation of pastures, co-grazing of pastures with less susceptible hosts. All of those can actually help with lowering of the parasite population on the farm. We know that restricting animals from grazing areas that are very wet, where the intermediate host or freshwater snail for liver fluke will prevent liver fluke infestations. Worldwide, reports of parasite resistance to anthelminth ticks, endectocides, and parasites are reported. And this will necessitate an implementation of a holistic approach or an integrated pest management program, wherein the systematic combination of multiple parasite management programs is employed to achieve sustainable and profitable parasite control. Every farm is unique. It will have to be custom-made for every farm. That is from my experience. I cannot tell one farmer what will work for you will work for another farmer. Changes in consumer preferences are also impacting beef production. For example, there's a shift towards natural, organic produced beef, and a portion of the consumers are well prepared to pay a premium for these products. Let's have a look at the effect of gastrointestinal nematodes on animals. Once ingested, of course, they can either feed on blood, for example, in the case of Haemonchus, or on other tissues and fluids from the mucosa like Ostertage or Ostertagi. And this results in decreased appetite, decreased gut retention time, a net fluid, electrolyte, and nutrient loss to the gut lumen, which negatively affects feed intake, growth rate, carcass weight, carcass composition, fertility, immune response, and mold yield. Ladies and gentlemen, there are many publications about this showing the effect that this has on animals. Severe infection can cause inflammation that we call parasitic gastroenteritis. And parasitic gastroenteritis is a watery diarrhea, animals suffering from anorexia, poor hair coat, and loss of body condition. More often, infection with GINs does not necessarily overt to clinical disease. And this is the problem that we have. Farmers don't see the clinical effect. They don't treat for what they don't see. but it rather causes subtle changes in production efficacy. And these production changes can be difficult to recognize. Data on the prevalence of Dictyocolis viviparus in Europe, Western Europe, indicate variable infection rates from 3% in Switzerland, 17% in Germany, 20% in Belgium, 63% in Ireland, and 80% in the Netherlands. The host inflammatory response to infection results in difficult breathing, coughing, noisy lung sounds, emphysema, and rapid loss of condition. It can also reactivate previous infections like bovine rhinotracheitis. Clinical lungworm is most often seen in young animals towards the end of their first grazing season. In Europe, of the annual economic losses due to helminth infections, including GINs, 81% was due to lungworms, GINs, and liver flukes, causing loss in production. Only 19% was due to the cost of treatment. Broad-spectrum anti-helminthics has always been the go-to products for nematode infection. But then, in the 1980s, the macrocyclactones came on the market. And very convenient, the potency, the efficacy. Man, it was the major breakthrough in nematode control. And then eventually the low cost of these products. We find them everywhere. What I've seen is in some countries there are more than 30 generic ivermectins registered. And anti-helminthic resistance due to, against these group of products is reported now worldwide. Anti-helminthic resistance makes reliance on the routine use of a single-class chemotherapeutics for effective control no longer dependable. And treatment failure due to anti-helminthic resistance can have a greater economic impact on cattle producers than no treatment at all. In other words, what I'm saying is, if there's resistance to a product, the farmer will be better off by not treating than treating those animals if you don't know what the resistance status is, because the treatment cost, the handling of the animals, the products itself contribute to the cost of the farmer. So alternative strategies for effective and sustainable control designed to limit production losses will have to be investigated. Knowledge of the unique anti-helminthic resistance landscape on individual farms, as I said, will be necessary for advising for economically sound deworming strategies. Fecal monitoring can, of course, play a role in that management of helminths. A meta-analysis of 170 research trials revealed elimination of deworming resulted in the US an increased cattle production cost of, in other words, where farmers stopped using elimination of deworming, farmers experienced a loss of $190 per head based on 2005 figures. Cost saving on production were greatest for cow-calf operations with savings of $165 per head. That is when farmers stopped treating for internal parasites. In a study of 6,320 Nelore calves, the return on investment for gastrointestinal nematodes with moxidectin in association with estrus synchronization, considering all input costs, was $44.9 per head for primiparous cows and $165 per head for multiparous cows. In a study conducted in Brazil, treatment of feedlot cattle at entering the feedlot with a single treatment of fenbendazole resulted in a net return of $14.6 per animal. If we look at nematodes, liver fluke parasitize, of course, a lot of animals, including cattle, and they are found in more than 70 countries worldwide. The prevalence is variable, up to 91% in Africa from 1.2%, 3 to 67% in Americas, 1 to 69% in Asia, 26 to 81% in Australia and Oceania, and then 0.1 to 86% in Europe. The most commonly encountered species is Fasciola hepatica, which is more commonly in your temperate areas, climates, but we will also find them in the tropical and subtropical countries. Fasciola gigantica, of course, is more prevalent in the tropical climates like Asia, Africa, and the Middle East. We know that Fasciola need a lemonade snail, a freshwater snail, as the immediate host to complete its life cycle. Once in the cow, the juvenile flukes migrate through the peritoneal cavity and then through the liver, and then they reach the bile ducts. And that will take up to 8 weeks. And that is also the time when these parasites cause the most damage to the animal or have the biggest impact. Within the host, the immature flukes cause trauma, inflammation, as they migrate through the liver. And then upon entering the bile duct, they cause bile duct obstruction and cholangitis. They complete their life cycle in 4.5 to 6 months, at which time they begin shedding eggs and contaminate pastures again. The geographical distribution of Fasciola species is limited to areas where the appropriate snail species, of course, is present. Areas with high rainfall, wet, marshy areas, poorly drained areas, and even certain soil types are more suitable for these freshwater snails. And the timing of fluke transmission varies in accordance with seasonal rainfall in each geographic area. Fasciolosis can cause financial losses to butchers and farmers due to liver condemnation, poor quality carcasses, reduction in growth rate, reduced productivity, and it can cause significant morbidity and mortality in beef cattle. More often, subclinical disease, mostly in your older animals. The acute, what we see at the top, is mostly in the younger animals. In the older animals, we see decreased feed efficiency, lower growth rate, lower fertility rate, and overall loss of production, which is not always recognized by the farmers. Losses in the feedlot result from reduced feed conversion rate, lowered average daily weight gain, and then a substantial delay in reaching slaughter weight. The worldwide annual losses in cattle due to liver fluke have been estimated as $3 billion. In one UK study, cattle with fasciolosis took on average 10 days longer to reach market weight compared to animals with no evidence of liver fluke. In a study of 160 Scottish farmers, liver fluke infection caused an average 6% reduction in profitability on an average beef farm. Production gains following treatment for liver fluke. In a review of 1,582 published studies, treating for liver fluke resulted in positive effects. If we look at that, there's 9% increase in daily weight gain, 6% increase in live weight, and 0.6% increase in carcass weight. In a large survey in Florida and the USA, control of liver fluke resulted in 8 to 10 kilogram heavier cows, 1 to 3% more calves, and 14 to 20 kilogram heavier calves at weaning, yielding a net return to the producer of $15.19 to $31 per brood cow, depending on the size of the crop and the calf prices. If we look at ticks, about 80% of the world's cattle population are affected by ticks and tick-borne diseases. Cattle in Asia, Australia, Central and South America are affected primarily by the cattle tick Ripicephalus, Biophilus microplus. And across Africa, there are a number of very economic important multi-host species. For example, Ripicephalus, Amblyomma, Ialoma. I live in a dangerous world. Ticks cause severe economic losses through direct effect, the tick worry that they cause, in other words, the irritation that they're causing, the direct irritation that they're causing to the animals, loss in productivity, injection of toxins, paralysis toxins by some tick species, blood loss from tick feeding, and indirectly as vectors for tick-borne diseases. If we look at production losses has been calculated for certain tick species. In the case of Ripicephalus microplus, We looked at 19 papers, and the production losses attributed to each individual engorged female was 1.3 grams body weight loss in Bos Taurus cattle and 1.18 grams per engorged female in Bos Taurus cross Bos Indicus. These two were not statistically significant, indicating that the treatment threshold number of ticks would be the same for these types of cattle. Production losses per tick for various cattle breeds have been calculated in a study of, again in Brazil, on Rhipicephalus microplus and its effect on cattle performance. It showed that tick infestations resulted in reduced weight loss. For example, in the backgrounding phase, $34.6 per head. And in the finishing phase for Brangus cattle and crossbreeds, $7.97 per head. They transmit a diverse array of pathogens, including, of course, as we already mentioned, protozoa, bacteria, and viral diseases. And some of these diseases have been listed as notifiable diseases by the World Health Organization: bovine babesiosis, anaplasmosis, theileriosis, and heart water. The cattle fever tick is considered as the economically most important species of them all, not only because of the diseases that they can transmit, and they are the vectors of Babesia bovis and Babesia bigemina, causing, obviously, babesiosis, but also because of the resistance that this tick species have developed or has developed against majority of caricidal products on the market. Estimates place bovine babesiosis at the top of the list of arthropod-transmitted diseases. In fact, we regard in some countries as the main killer of cattle on pastures. A meta-analysis from 81,000 samples from 62 countries across 6 continents revealed the overall global prevalence of bovine babesiosis as 29%. If we look at it per region, 52% in North America, 64% in South America, 61% in Australia, 22% in Europe, 27% in Africa, and 19% in Asia. Only babesiosis, the prevalence. Other tick species, of course, can also transmit tick-borne diseases. For example, anaplasmosis can be transmitted by more than 20 different multi-host tick species, of which the Rhipicephalus and the Mesentos species are the most important. In East Africa, I say there in Tanzania, but it's actually Tanzania, Kenya, Uganda. I've been in those countries doing some work on East Coast fever, Malawi, Zambia, and it's actually spreading now to the south towards Zimbabwe as well. Rhipicephalus appendiculatus, what we call the brown ear tick, is the vector of the protozoan parasite called Theileria parva, or East Coast fever, deadly in cattle. I've been to farms where a farmer has lost almost 100 cattle over a 30-day period because of East Coast fever and inefficacy treatment. It has a major impact on livestock in Africa, causing up to 1 million cattle to die every year. That's about 1 dead animal every 30 seconds at a cost or a loss of about $380 million, just one disease. The engorged female from this tick species causes weight loss of almost 4 grams per day. There's evidence that ticks and tick-borne diseases are increasing. Native species are expanding their regional range, and exotic species have been identified in unfamiliar geographies. The Lone Star tick is expanding its range in the United States. The Asian longhorn tick and the red sheep tick have been identified for the first time in the Western Hemisphere. And Rhipicephalus microplus was discovered in Ivory Coast in 2002 and is now gradually finding its way down West Africa. This tick species, Rhipicephalus microplus, was introduced to South Africa in the 1960s. Now, we have what we call the indigenous single-host tick, Rhipicephalus decoloratus. And what has happened now is this tick species is now basically killing our indigenous tick species. There are research articles showing that when the male from Rhipicephalus microplus breeds with the female from Decoloratus, that female is infertile, and vice versa. But the males from Rhipicephalus microplus is dominant to Rhipicephalus decoloratus. So what they're doing is they're taking over, causing thousands of cattle to die from babesiosis, Babesia bovis, in the country at the moment because of no immunity. And this tick species, which is also called the subtropical cattle tick, is now even found in Namibia. Guys, Namibia is a desert. That's not the usual, normal habitat for this tick species, and they survive there. I always say ticks have learned to survive under circumstances that was not normal to them. When I started working in the southern parts of South Africa, I was told in the late 1980s that this tick, or the Singalose ticks, is not, you won't find them further than 70 kilometers land in. 10 years later, I did a farmer's day talking to farmers about 400 kilometers inland. And I couldn't believe how many animals they were losing because of babesiosis transmitted by Singalose ticks. And that area, guys, in winter is extremely cold, which is not the temperatures that these ticks prefer, and they survive. In 1906, the United States government initiated a Rhipicephalus microplus eradication program intended to eliminate babesiosis. And at that time, the production losses due to babesiosis was $63.25 million annually. And when they eradicated babesiosis, the subsequent savings were estimated to exceed $3 billion annually. From a loss of $63.25 million annually to a profit or savings of $3 billion annually. Return on investment was $98 for every dollar spent by the farmers. In 1996, the worldwide economic losses due to ticks and tick-borne diseases were estimated to range from $13.9 billion to $18.7 billion per year. And by mid-2000, 4 years later, it increased from $20 billion to $30 billion per year. Tick control has relied primarily, again, on the strategic use of parasites, and these chemicals prove to be very effective. Farmers, the first thing they will do is when they see ticks is they go to a wholesaler or a veterinary and they buy the can and they go and treat the animal. However, the routine treatment and indiscriminate use, inaccurate dosing by farmers, especially with Rhipicephalus microplus, cause these ticks to develop resistance, not only against one class of actives, but also against multiple classes of actives. And the resistance to most chemical classes, including organochlorines, organophosphates, carbamates, formamidines, pyrethroids, and macrocyclactones, has been reported all over the world. Occurrence of parasite resistance requires, therefore, a new way of thinking. Alternative methods will have to be implemented. The use of naturally resistant cattle. We can select for individuals in the same breed, in the same species, that are more resistant to parasites than others. Those ones that need multiple treatments and regular treatments because of their susceptibility, I always say to the farmers, get rid of them. Sell them to your neighbor if you don't like your neighbor. Send them to the slaughterhouse. Keep the ones that require less treatments. There's biological control, grazing management for tick populations, and then, of course, using vaccines. The economic threshold for when to treat, and very often, the farmers ask the question, but when should I be treating for ticks? How many ticks is needed on an animal before treatment is actually required? Because we don't want to eradicate. We don't want to attempt to eradicate parasites. Ladies and gentlemen, these parasites have been with us since the creation of Earth. And don't tell me that we are going to eradicate them. It will never, ever happen. And in such estimate, a mean of at least 100 Rhipicephalus microplus engorged female ticks is necessary for treatment to be profitable. It obviously depends on what diseases they may transmit. If there's babesiosis, it may be less. So for every farm, we have to do a proper audit and estimates to make the recommendations. A study of Rhipicephalus microplus control and its effect on beef cattle performance in Brazil showed that tick infestations resulted in reduced weight gain. In the backgrounding phase, $34.6 per head. And the finishing phase for Brangus cattle, I think we've already mentioned that, is $7.97 per head. The cost of treatment ranged from $0.55 to $2.25 per animal, depending on the treatment. A return on investment for Nerori cattle was lower than for Bos Taurus breeds because of these animals being affected less by the ticks than the Bos Taurus breeds. Using bioeconomic modeling, Calvino investigated the profitability of controlling Rhipicephalus microplus on cattle compared to no-tick control. Under extensive farming, it was $22.62. Semi-intensive farming, $13.9. And intensive production, $28.29. That's a net profit between herds with tick control and those without tick control. If we look at production type, parasite exposure, infection, and disease will differ by geography, class of cattle, and also the associated management practices. The goals for treating for parasites differ upon the goals of the producer. In some regions, simply to prevent mortalities. In some areas, it is to optimize productivity or production. The selection and use of anthelmintics and acaricides based on parasite prevalence, resistance profiles, along with appropriate timing of administration, is key to successful implementation. If we look at cow-calf operations, all cattle on pastures are more exposed to gastrointestinal nematodes, and productivity is measured by pregnancy rate, average daily gain, and calf weaning weight. In a review of 170 research studies in the US, 73% of cow-calf operators utilized dewormers and 81% for fly control. Cost savings on production were greatest for cow-calf operations that used dewormers, with savings of $165 per head. In a 2-year study by Stromberg, the average daily weight gain for calves and reproductive performance were both significantly greater than untreated animals. Parasite control with dewormers increased weaning rate with 23.6%. The pregnancy rate average across both years was 94% for treated cows compared to 82% for untreated animals. The effect of parasite control of dewormers on pastures. It also significantly reduced parasite shedding and pasture contamination. In a large survey of cattle producers, I think we have already done this one. If we look at feedlots, since nematode infections in feedlots is not a problem, treatment with a short-acting anthelmintic at entering the feedlot have been shown to improve weight gain and carcass grade. By not doing deworming, stocker cattle and feedlot cattle production costs increased by $21 and $22 per head, respectively. Cattle infected with liver fluke have increased average daily weight gain and feed efficacy. Has decreased average daily weight gain and feed efficacy, poorer carcass quality, and lower prices compared to uninfected cattle. Conclusion: production losses due to parasites can be significant and negatively impact the quality of meat produced, necessary for an increased population. Losses increase the cost of meat production and result in diminished financial returns for beef producers. By implementing strategic parasite control measures, this is the key today, with thorough knowledge of parasite risk, prevalence, parasite resistance profiles, and prices can result in positive economic returns for beef cattle farmers in all sectors. Ladies and gentlemen, thank you very much Muchas gracias.
Thank you very much, Dr. Strydom. I think this was a very enriching lecture regarding the negative impact of parasites, which has been definitely underestimated for several years. So thank you very much. We thank Dr. Strydom. And we will continue with the scientific conferences. We will have Cintli Martínez-Ortiz-de-Motellano. She's from Mexico, and she will be presenting Mezquite pod as a potential nutraceutical for the control of Haemonchus contortus. Welcome, Cintli.
Thank you. Thank you, Elke. Well, good morning. I'm pleased to be here to discuss our work. I would like to begin by express my gratitude for your interest in our country, in our peninsula. And as introduction, sorry. Okay. As introduction, the parasitism problems are almost associated with poor nutrition. Gastrointestinal nematodes here in Mexico is the second health problem in small ruminants. Haemonchus contortus is the most pathogenic nematode known, and the deworming practice is always bound by a set of factors. These factors These factors are lack of weaning, abuse of molecules, like Dr. Tom said, and antibiotic resistance. This is a result of this abuse and these factors. The following video, no sé si me pueden ayudar a ponerle play, por favor. Gracias. The following video presents an example of a post-treatment haemonchosis that was identified at necropsy. So you can see the inflammation of the mucosa and the parasites adults and the parasite burden. So this is our day-to-day in worldwide. So this is an example of an animal. As Dr. Tom say, we need attend this phenomenon of antibiotic resistance by different approaches, and the sustainable integrated parasite management, it's by definition a major option. It's a combination, like Dr. Tom says too. I don't repeat the name, but you can see this scheme. And this management is on the basis of three fundamental principles. One is enhance host response against GIN. Two, reduce the GIN or deplete the source contamination in the environment. Three, reduce the GIN population within the host. And we focus this work on the third use of nutraceuticals. What is a nutraceutical? It's a food, it's a livestock feed, it's a nutritional product, but also a treatment of disease. It's a combination. In my experience, the best example of a nutraceutical is Les Enfants. In English, it's a healthy hay, and I was a part of the Healthy Hay project, and we worked with, and we had excellent results. But this bioactive plant is in Europe. So why mosquito pod? It is nutraceutical in Mexico as a resource of high nutritional quality, primarily composed of protein. The low cost and easily accessible coincides with the highest small ruminant production in our country. So the geographical location is a key. In the other hand, the pods grow in a short period on the year, so we do not risk ecological pressure on the pastures. So we consider that it's a sustainable vegetable or no vegetable, a plant. So finally, it's important to say, if we want to select a plant as a nutraceutical, we must take into account these 6 steps. Our work is in the first step, the in vitro assay. So our objective is demonstrate in vitro anthelmintic activity of mosquito pod in extract on infective larvae of Haemonchus contortus. The road is long but promising. The methodology was carried out with 4 specific objectives: to make a strain of Haemonchus contortus culture, to have mosquito pod collect, to perform the larval migration inhibition assay, and the larval excitement inhibition assay. We culture following the procedures of Corticelli Lai and 2 strains of Haemonchus contortus, one of Universidad Nacional Autónoma de México. This strain is sensitive to ivermectin, and the second in Universidad Autónoma de Yucatán, and this is multi-resistant, including ivermectin. From mosquito pod collected, okay. So we take from Oaxaca. The extraction pods were dried the pods were dried in the faculty of the UNAM, and the extraction and phenol quantification was in the laboratory of nutrition in the same university. We use Folancical technique in order to get the total tannins. And so we obtain more than 80 micrograms per milligram of dry matter of total tannins. So we determine that Mezquite pod is a bioactive plant and rich in tannins. To test the biology of hydrotropism and geotropism of the larvae was used larval migration inhibition assay. This is a scheme image of the assay. So we start with the incubation of the larvae solution with different treatments, including different concentrations of mosquito pod extract and also ivermectin and levamisole. Before we place 0.5 microliters of the different treatments in a 48-plate cell culture plate with a 25 microns mesh insert. 3 replications were made. Before 3 hours of incubation, we observed the percentage of migration. If we observe inhibition of migration, the effectiveness is inexistent. So we use another assay in order to observe the development of Haemonchus contortus life cycle. So this is a larval excitement inhibition assay. The same incubation of the larvae solution with the different treatments taking place. And during 60 minutes, we observed the percentage of excitement of the L3 larvae. In different moments, 0, 20, and 40, and 60 minutes. And finally, we observed the larvae solution. If the larvae is naked, there are not the effect. This is our results. For the migration inhibition assay with the UNAM strain, we start to observe an effect since 150 micrograms of mosquito extracts. a very near results with effectiveness of levamisole and ivermectin. Contrary with the Wadi strain, we didn't have the same results. And the effectiveness of Mezquite pod was poor, around 20 and 40%, and we didn't test the ivermectin. For the test of achievement, we could see in the figure the polar scenarios. Near 100% in the top of, I don't know how to, yes. In this polar, we observe near 100% of achievement larvae at 60 minutes in water, and 100% of larvae in levamisole died. The achievement was, inhibition was placed in the 40 larvae with different extracts. And so we didn't have the ideal Mezquite pod extract effect. But we observed a paralyzed effect. ¿Me pueden ayudar con el video, por favor? And this is an effect that we need to investigate. So Mezquite is a bioactive plant rich in tannins with nutraceutical potential. Mezquite inhibits motility. We need to study the resistance and susceptible stains. Also, we need to study the extracts like ethanolic or lyophilized way. We had acceptable percentage of inhibition of migration, but we need more studies. We need also to complement it with more concentrations, and the achievement was not inhibited. And we observed this paralyzing, but we need to respond this answer. We need more studies for it. No studies of pod extracts were found. We observed larvicidal effect in similar, in other studies with plant leaf. As a prosopis, we are still investigating the compounds of total tannins and the probable identification of specific molecules, like monomers or dimers, etc. As well as the synergies and antagonistic actions, the Mezquite bicompounds may have with bicompounds common of ruminant nutrition. And we find studies in Brazil and Kenya with another species like Prosopis juliflora with an anthelmintic effect. Our novel approach is horses also eat Mezquite. Horses also have gastrointestinal strongylid nematodosis, specifically cytostomins. There are more than 50 species of these strongylus mixed with Strongylus antrodontophorus. And now tests for in vitro effect of this complex parasitic population are currently underway. This is a Mezquite nutraceutical potential reflection. This is a photo that one friend take me. If humans eat a delicious flavored ice cream of Mezquite pod, we can do better and think about integrating it as a nutraceutical within a One Health approach. The name is Pechita. So thank you for listening and be patient with my English. And if you have a question, I'm here.
Thank you very much, Cintli. Well, without a doubt, the use of plants nowadays or for the past 10 years has been catching our attention, and it has very interesting results. So we have room for a couple of questions. I don't know if someone has a question for Cintli regarding the use of Mezquite. Go ahead, Dr. Rosiles, please. Yes, please.
Yes, I like to answer the question. If there is any difference according to the covering of the seeds, or is different quality of nutrition between seeds and the covering? Am I clear on asking what the covering means? I mean, in Mezquite, you got a pot, okay?
Yes, yes.
And there's seeds inside,
Yes.
and there's the covering.
Yes.
I was kind of thinking it might be any difference between the seeds and the covering of the seeds.
Okay, this is
Have you read any studies looking or talking about the difference in nutrition quality between the seeds and the outside of the seed?
No, doctor, this
So
is
you have to eat all of it.
Yes,
Okay,
this is a good
that's it.
question. Yes, this
Thanks
is
a
a
lot.
good question. Thank you, Dr. Rosiles.
Thank you very much. Another question?
No.
Go ahead, please.
Hi, my name's Melissa George. I'm from Australia.
Thank you.
Congratulations on your work. And
Thank you.
in vitro assays for detection of efficacy are extremely challenging. So doing the larval migration inhibition assay and the achievement assay, that's a lot of work. But there's also alternative assays in terms of larval development assay, motility-based assays, those types. So can you explain a bit why you chose the LMIA and the achievement assays?
Okay, it's simple. We had the material for to do, but we need to do another essays. That is important because if you say we can also even larval achievement inhibition assay didn't work, but we don't know why. So yes, we need to do more essays.
Thank you.
Thank you.
We have room for a couple of questions. 2 more minutes.
You can buy the ice cream in Hermosillo, Sonora. No?
No?
So,
Thank you very much,
no,
Cintli.
thank you.
Dr. Gabriel. I'll present you here. Welcome to Gabriele Maier. She'll be giving her lecture on comparisons of single versus combination of dewormers on fecal egg counts and weight gain in young grazing cattle. Welcome.
Thank you for that introduction. I apologize if my voice is a little bit scratchy. I did try to talk over the mariachi last night, which may not have been the best idea before you give a talk, but let's see how it goes. So as we have heard from Dr. Strydom about the many benefits of deworming, treatment for intestinal parasites is very common in grazing cattle because of all the perceived benefits like improved immune status, increase of weight gain, better reproductive performance. But as he also pointed out, testing is not very common. So this little bar chart is from a study by the USDA, United States Department of Agriculture. They have a service called National Animal Health Monitoring System, and they do surveys of different commodities, and this is from a cow-calf survey where they asked whether producers had done any testing for parasites, for intestinal parasites, in the past 3 years. And what they found was that even in larger herds of 200 cattle or more, it was only 12%, and particularly in the smaller herds of up to 50 cows, it was less than 4%. So in the US, we have 3 classes of anthelmintics available to us to treat beef cattle, and those are the benzimidazoles, the nicotinic agonists, as well as the macrocyclic lactones. So the Food and Drug Administration has recently introduced or asked producers of anthelmintics to add a statement, a warning statement on the label that warns about potential resistance to dewormers. They also say that dewormers should be used in conjunction with other parasite management control measures, and they point out that it is good to perform fecal egg count reduction tests to test for resistance. And so this fecal egg count reduction test is performed in the following manner. You collect feces from 10 cattle at the time of treatment. An egg count is performed, and then you come back approximately 14 days later. It depends a little bit on the drug used, and you perform a second egg count. And if the egg count reduction, so the reduction of eggs found between the two time points, is 95% or more, as well as the 95% confidence limit, the lower limit of the 95% confidence limit is at least 90%, that's considered normal. That's considered as an efficacious dewormer. It is doubtful if either one of those thresholds is not met, and it is considered reduced or evidence of resistance if both of those targets are not met. So the use of combination treatment, so that means using two drugs at the same time that are from two different classes, is now considered a way, one of the tools in the toolbox to combat resistance of intestinal parasites. And this has been shown to be successful in previous trials in controlling nematodes. There's also a new product available on the market in the US. And actually, I think the next speaker is actually going to be presenting on this very topic. It is a combination of doramectin and levamisole. And experts, parasitologists, veterinary parasitologists agree that this is a good way to use these wormers in combination. So here is a chart. It's a little bit busy, but I'll walk you through it. So this was preliminary data that we collected between March and August in 2021. So we went out and we wanted to see whether there is any evidence of resistance in California. So I'm from the University of Davis in California, and there are not that many studies from the Western United States on parasite loads and resistance in particular. And so we enrolled 11 herds, and we tried to meet that goal of 10 cattle, but what happens is if you come back 2 weeks later and you have the same 10 cattle waiting in the alley, they don't wait to defecate until they're in the chute, so some of them we just couldn't retrieve any feces, so some of them we fell short a little bit. They were about a year old, so they were weaned cattle but still growing. And the pre-treatment range of egg counts was between 8.9 for herd number 10 and 243 for herd number 5. So quite a range. And what we found in terms of a fecal egg count reduction when we came back was that almost none of the herds met those goals. So all of them were actually in the category of reduced, except for one. So these are our take-homes from this preliminary trial. All producers, 100% of those that we visited, used one class, macrocyclic lactones. The initial egg counts varied quite a bit, and only 1 in 11 herds achieved the desired egg count reduction with the method that they used. So I don't think I mentioned that these producers could use whatever they wanted to use at that time. So after we realized that there is evidence for resistance, I wanted to see, well, maybe if we use a combination treatment, we can achieve better results. So the objectives for this study were to use a combination treatment of macrocyclic lactones and benzimidazole, so two wormers from two classes, versus single treatment with macrocyclic lactone alone, and to see the effect on fecal egg count reduction, as well as on weight gain in the form of average daily gain. Our enrollment criteria were cattle that were between 6 and 18 months old. We enrolled a total of 322. from 6 herds in Northern California between July 22 and June 23. They had to have no history of deworming in the 45 days prior to enrollment, or 150 days if they had used long-acting eprinomectin. We wanted to see an egg count of at least 200 total eggs in fecal samples from the animals that we tested in each group. So that's a combined, so not an average, a combined of 200. And we randomly assigned these cattle to 2 treatment groups, so they would receive either 200 micrograms of injectable ivermectin or the same dose plus 5 milligrams per kilograms of oral fenbendazole. So we collected about 50 grams of feces per rectum from up to 20 per group. So we had learned our lesson. We increased the sample size on the day of enrollment and then came back 2 weeks later. And then we assessed for trichostrontial type eggs with the mini FlowTech system, which is more sensitive than the conventional McMaster's test. We also performed a coproculture on pooled samples from each treatment group at both sampling time points, and then we weighed them on the enrollment day, and then we came back whenever it was convenient for the producers to gather these cattle again, which was 2 to 7 months later. For the analysis, for the fecal egg count reduction test, we used the 10 animals in each group with the highest egg counts. And then we used an online calculator called Modeling Fecal Egg Counts with Shiny. And that is based on the R package egg counts, 2.3, and it uses a Bayesian hierarchical modeling system. For descriptive analysis and body weight, we used linear mixed models in SAS, where the herd was the random effect, and we also offered age and pasture type to the models, and pasture type is either irrigated pasture or dry range. So these are the results, these are the descriptive results from the 6 herds enrolled, the number of cattle enrolled, how old they were, so they were between 6 and 15 months of age. The I stands for irrigated pasture, the D is for dry range, the average weight at study start for the 2 groups, how long we waited before we weighed them again, the end weight, and then the average daily gain for those 2 groups. Herd number 5 and number 6 were not followed further, and I will get to that on the next slide. And so as you can see, the average daily gain, they're all pretty similar between groups, and I can let the cat out of the bag now. We did not find a difference in weight gain, in average daily gain between our treatment groups. So here is the result from the fecal egg count reduction. So we have the different herds. We have our sampling intervals, so we were a little bit better. One herd, they just couldn't do it in 14 days, so we had to do it after 20 days, whether they were on irrigated or dry pasture. And then the reason why we didn't follow herds 5 and 6 was because they had at enrollment a fecal egg count of either 0, so no eggs whatsoever in any of the animals we sampled, or 1, so there were a couple that we detected 5 eggs per gram. So they didn't meet our enrollment criteria, so they were no longer followed. So there was, again, a range of eggs per grams at enrollment. And then, as you can see, for the fecal egg count reduction that was achieved in our control group that only received ivermectin, again, none of them achieved the normal range that I showed you earlier. However, in the combination group, all of them achieved the normal range. So they were all over 95% reduction. The 95% confidence interval, or it's an uncertainty interval with the Bayesian modeling, was over 90% in each instance. And this is the result from the coproculture. So most herds started out with a predominance of Cuperia species, but there were a couple herds that started out. This herd, number 2, actually started out with mostly Ostertasia, but then after treatment, it was mostly Cuperia. The same down here. They also had a fair number of Osteotagia initially, but then after treatment we found mostly Coperia. And then I also want to draw your attention to this herd, number 3. In the treatment group, they actually had an increase in Osteotagia. However, this result is only based on an egg count of 8 eggs per gram, so it's a little bit hard to interpret if this is significant or not. So these are the results from the least square means for average daily gain after 2 to 7 months. So in the control group, it was 0.57 kilograms. In the treatment group, it was 0.59 kilograms, plus minus 0.15 kilograms. So not significant. Pasture and age were also not significant in these models. So basically, we found that the combination of these 2 drugs was highly efficacious in reducing fecal egg counts. This was also found in another study from 2018. They used different drugs. They used doramectin and albendazole, but basically the same classes, and they found the same results. They followed one herd over multiple time points and followed them a little bit more closely, and they found that this effect of the reduced egg counts persisted for 2 months. However, after 3 and 4 months, that went away. They actually found an increased weight gain in the combination treatment group, but not average daily gain. So when you look at the statistics, average daily gain between the combination treatment versus single treatment, there also was no difference. It is important to understand that egg counts are not the end all. So they do not reflect intestinal nematodes one-to-one. So it's not necessarily a great indicator for clinical disease. We have to think about fecundity. So Osteotagia is a low egg shedder or a low egg producer, but it is the most important in pathogenicity. I have not been able to find good thresholds for when to recommend treatment. So I'm still at a loss to really advise my ranchers when they should be treating and when they should not be treating. It is a fine balance between avoiding weight loss and also exposing the animals to these parasites so that they can build up resistance. However, the fecal egg count reduction test is still a very good tool to assess resistance. And we can use it in this way. So we also found that resistance is mainly driven by the species or the genus Coperia, but we should also keep an eye on Osteotagia, especially because it is the most pathogenic. So in conclusion, the current practices, at least in my neck of the woods in California, but probably across the western United States, and this is also in line with what Dr. Strydom's experience is that whatever producers are doing is this indiscriminate use of macrocyclic lactones without testing. It's not efficacious. We have evidence that we have resistance. These combination treatments may help us. It may be a good tool in the toolbox to prolong the time to build up for resistance. We did not see the weight gain differences that we were expecting between the treatment groups, despite the results. But however, we also waited at least 2 months, so these weight gain differences may have been apparent at earlier time points. And also with different parasite species might have been different, and we do need better strategies to deworm cattle. So with that, I want to thank my funding sources, the USDA NIFA, as well as Merck Animal Health for in-kind donations, my collaborators from University of California, Agriculture and Natural Resources, and the Texas A&M Diagnostic Lab for excellent technical services. So I'll leave up my references and I will take questions. Thank you very much.
Thank you very much, Dr. Gabriele. A real problem nowadays, anthelmintic resistance.
Yeah, just a little one.
Please.
Dr. Maier, there you go. I'm so sorry, I don't know if I interpreted your data around the copper culture differently. It was a little bit difficult for me, but
we can go back.
When you look at the copper culture, did you seem to find any evidence of potentially double resistance against both macrocyclic lactone and the febendazole that you use in that particular study?
Sorry, can you say the question again?
Whether you find any evidence in this data of double resistance both to the macrocyclactone, to ivermectin, and to the febendazole?
Oh, yeah. Well, okay. So if we look at the results, so on the left side we see the control group that was just a macrocyclic lactone, and obviously, Coperia seems to be like thriving under that pressure. For the treatment group, so we had 2 herds where no larvae were found whatsoever. So I think that's good news. The herd number 3, that was also a herd that had a fairly high burden. That was the one that started out at around 500 or 600 X per gram. Yeah, we do see, we see that there were some survivors in both Coperia as well as Ostotagia, and that is worrisome. I absolutely agree. So that's why I'm thinking we do need to keep an eye on that, that there may be double resistance already.
Thank you.
Thank you.
Thank you very much. Another question? Go ahead, please.
Thanks for your presentation. With the introduction of the mini flow tag, I think it's great that you use that in your analyses. You made a comment about you don't recommend basically treating at certain thresholds, and I think that maybe older parasitologists would have used to recommend some certain thresholds, and now that we're using the mini flow tag and it's much more sensitive, we're getting higher fecal egg counts maybe than before. Could you comment a bit about how use of the mini flow tag might change some of those interpretations and maybe extend a bit on why you don't recommend treating on thresholds?
Yes, well, it's a good but difficult question to answer. So the mini flow tag has a detection limit of 5 X per gram, while the McMaster's has one of 50. And so basically if you find 1 egg in a McMaster, that could be 50. But if you find 0, that could be 49, or anything below 50. So it's just not a very good test for cattle. It's much better for small ruminants because you tend to have higher shedding. The mini flow tag is a great tool. However, it is not offered. So in the United States, it is only offered by one diagnostic lab in Texas. That's the only lab that offers this test, as far as I could find out. So we still have a ways to go. I'm hoping that more of these labs will go and come and offer this test. I know Merck also has kits that they send out to producers, and they can test for free. So that's another option. But essentially, yes, I mean, producers in the US have very little in terms of testing potential possibilities. If they use this McMaster's test, it's not super, it doesn't tell us a lot. So again, I have had discussions with parasitologists, and I'm sorry, I'm running out of time. I would recommend, in a case where you have 0, where you cannot retrieve any eggs, I don't think they need to treat. And the rest needs to be adjusted, just like Dr. Strydom said. Thank you.
Thank you very much. Right now, Jase Ball, welcome. We'll be having the conference on growth performance of beef heifers treated with an injectable fixed dose combination or single active endectocide. Welcome, Jase Ball.
Thank you very much. So in the agenda for the presentation today, we'll start with a background and objective. We'll then move into an overview of Valcor, followed by results, and then we'll move into a summary and conclusion. So as the previous presenter, as well as others today, have shared, in the literature, there has been plenty of concern about resistance to today's gastrointestinal nematodes. And that increased resistance has shown to negatively impact the performance and weight gain of beef cattle. And so DeRosa and others have hypothesized that combining actives from different antiparasitic classes can improve treatment efficacy against today's gastrointestinal nematodes by improving herd health and productivity. Therefore, our study objective was to determine the effectiveness of a new doramectin and levamisole combination endectocide, trade name Valcor, compared to ivermectin on the growth performance of beef heifers sourced from the southeast United States harboring a natural gastrointestinal nematode infection over a 56-day period. So in an effort to combat the resistance from single active anthelmintics, Valcor combines doramectin, a macrocyclic lactone, with levamisole and imidazothiazole in a new fixed dose combination. That combination volume is 1 ml per 25 kilograms of body weight. Within that combination, it brings in 0.2 milligrams per kilogram of doramectin and 6 milligrams per kilogram of levamisole. So moving into our materials and methods, for this study we utilized weaned crossbred English Continental heifers that were 6 to 9 months of age with a day zero body weight of about 520 pounds. That body weight ranged from 346 to 915 pounds. They were all sourced from the southeast United States. All came from auction markets within the state of Alabama with no known history of deworming treatment. The two treatments we utilized for this study were the fixed dose combination of doramectin and levamisole, which I'll refer to as Valcor for the remainder of the presentation. And we enrolled 773 heifers on that treatment. The second treatment was ivermectin. We utilized generic doramectin as the pioneer was having supply problems at the time, and that dose was at 0.2 mg per kg of ivermectin, another macrocyclic lactone, and that dose volume is 1 ml per 50 kilograms, also injected subcutaneously, and within that treatment we enrolled 773 heifers. The primary variables for this study, this was a production study, so the primary variables were average daily gain, total weight gain, an interim body weight on day 14, and a final body weight on day 56. The secondary variables are going to be our parasitology variables, including fecal egg counts and our coprocultures. And the study was conducted in the Texas Panhandle at a backgrounder grower facility. Animals were housed in 50 head pens, and the study was conducted in 4 separate cohorts. To meet inclusion criteria for enrollment, cattle had to have at least a fecal egg count of 30 eggs per gram on arrival. And across the study, we brought in 2,091 heifers. We ended up enrolling 1,548, but the mean fecal egg count was 240 eggs per gram with a range all the way up to 27,000 eggs per gram. So a very highly parasitized group of heifers here. Moving into the study timeline, these heifers arrived to the backgrounder facility at least 21 days prior to study start, which initiated our acclimation phase. At that time, they were treated on arrival. They were vaccinated against with multiple respiratory vaccines, as well as a clostridial vaccine. In addition, we metaphylactically treated all of these cattle with an antibiotic in an effort to try to control some of our bovine respiratory disease in this highly parasitized group of heifers. We also recorded arrival body weight, and we checked these cattle for the presence of an implant. If they had an implant, it was removed, and the cattle were not implanted for the duration of the study. And then day -19 to -5, we collected fecal egg counts on all cattle that arrived to the facility, and I already shared that data. We also included taking a body weight. We blocked by body weight, so the body weight, as well as that inclusion criteria of meeting 30 eggs per gram, was used to generate the allotment. On day 0, animals were treated with either Valcor or doramectin. We recorded an initial body weight, and then we fecal sampled 10% of each treatment, so not all of them, but only 10% on day 0, and they were then moved to their pens per the allotment. On day 14, we collected an interim body weight, and then those animals that were fecal sampled on day 0 were sampled again to determine fecal egg count reduction. We also conducted a feed weighback in an effort to determine dry matter intake for that period. Dry matter intake was done across treatments. Treatments were commingled within pen so that we only understand our dry matter intake across the 2 treatments. Then our final body weight was collected on day 56, and then we followed that with a weighback to determine overall intake over the course of the 56-day study. This study was done prior to approval in the U.S., so we had an investigational food use authorization So cattle that were on the Valcor treatment remained on site until day 70 when they met the investigational food use authorization, and then they were returned to herd. This ration that we fed these cattle ad libitum, it was a typical grower ration for the Texas Panhandle, very dry ration that was predominantly corn and alfalfa hay. In addition, we did include Bovatec or Salicid in the diet at 30 grams per ton in an effort to try to control coccidiosis. The ration proximate analysis, again, very dry ration at over 80% dry matter. Crude protein was about 16%, and our net energy of gain was 1.04 megacals per kilogram. Just to say that the ration met and exceeded the nutrient requirements of the study cattle for this study, and that'll be indicative of some of the performance data I share in a little bit. The experimental design was a randomized complete block design that we replicated in multiple pens and cohorts. Our treatments were blocked by that pre-randomization body weight on day minus 19 to minus 5, and animals from the same block were housed in the same pen. So our treatments were commingled, equal representation of each treatment in each pen, which allowed us to use animals that are experimental unit. Our average daily gain and total weight gain data, we collected both deads in and deads out data. Today we're only going to share the deads in data. However, I want to point out that the interpretation from the statistics does not change whether we look at it from a deads in perspective or a deads out perspective. From a stats perspective, our growth performance and fecal egg count data were analyzed using a general mixed model with repeated measures in SAS. With our fixed effects of treatment day and the interaction of treatment and day. Our random effects are listed there. Our fecal egg counts were log transformed prior to analysis, and significance was declared at an alpha of 0.05. Moving into our results, I'll try to set up this table for us. We're going to look at fecal egg counts first. We'll first look at day 0, move left to right. Again, we only sampled 10% of each treatment. So for Valcor, we sampled 78 head for fecal sampled, 78 head for Valcor, and 79 for doramectin. The arithmetic mean for Valcor was 291 eggs per gram compared to 250 eggs per gram, with a range for the two treatments all the way up to about 2,000 eggs per gram. And statistically, when we look at it from a geometric least squares means basis, there was no difference between the two treatments on day 0 for fecal egg counts. Now, if we move to our day 14 fecal egg count data, again, the same animals were sampled on day 0 and 14. The arithmetic mean for Valcor was 0.33 eggs per gram compared to almost 64 eggs per gram for doramectin. I also want to point out, of those 76 head sampled for Valcor on day 14, only 2 had a positive fecal egg count, one at 10 eggs per gram and one at 15 eggs per gram. However, for the doramectin treated group, 65 of those 79 had a positive fecal egg count on day 14. And if we look at the change from 0 to 14, the fecal egg count reduction test, as Dr. Maier in the previous presentation mentioned, there was 99.9% reduction in Valcor treated heifers, whereas we only saw 85% reduction in the doramectin treated heifers. And if we look at it statistically from a geometric least squares means basis, there was a significant reduction in day 14 fecal egg counts for doramectin treated heifers compared to for Valcor treated heifers compared to the doramectin treated heifers. Next, we'll look at our culture data. So once we took fecal samples of those 10%, any heifers with a fecal egg count greater than 10 eggs per gram was then pulled to do cultures. We did 2 per cohort per treatment, so a total of 8 per treatment over the 4 cohorts. And so what we want to share here, all genera within a genus is listed. As with the previous presentation, the most prevalent genus was Cuperia for both treatments across both days, as we would expect of these cattle coming out of the southeast U.S., as well as some Ostrachausia and Trichostrongylus. If we look at it from a cohort perspective, so this is culture on a percent of larvae identified by cohort. What I want to point out here, so for Valcor here, across all 4 cohorts, Cuperia was our most prevalent genus. However, if we look at day 14, you'll see a lot of zeros. That's because 3 of the 4 cohorts, we did not have any larvae identified, as we didn't have any positive fecal egg counts. Only cohort 4 had positive fecal egg counts, as I mentioned in the fecal egg count data, but it was still predominantly Cuperia. Interestingly enough, for the doramectin treated group, the first 3 cohorts, the most prevalent genus was Cuperia. However, for cohort 4, we saw that actually Trichostrongylus had the greater prevalence within that cohort. But if we look at the day 14 data for the doramectin group, we saw that increase back with Cuperia, indicating some resistance there to Cuperia. We'll now move into the performance data, the primary variables here. Average daily gain we'll discuss first. So for the first interim period of days 0 to 14, Valcor significantly improved average daily gain compared to doramectin with a 0.095 kilogram per head per day advantage. If we look at it from the second interim period from day 14 to 56, Valcor significantly improved average daily gain again with a 0.07 kilogram per head per day advantage. And if we look at it holistically over the 56-day study, Valcor improved average daily gain by 0.076 kilograms per head per day compared to the doramectin treated heifers. If we look at that on a total weight gain basis, the statistics remain the same. Highly significant improvement in all 3 of the periods, with Valcor improving total weight gain by 1.33 kilograms in the first 14 days. The next 42 days, a 2.892 advantage. And then over the course of the 56-day study, Valcor improved total weight gain by 4.22 kilograms compared to doramectin. Lastly, and most importantly, we wanted to look at this from an economic standpoint. So we initially looked at the weight at day 0 and day 56, and then we calculated weight gain by subtracting the day 0 weight from the day 56 weight, as indicated in the total weight gain slide. But Valcor cattle or heifers gained 76 kilograms over the 56 days compared to 71.96 or 86 in the doramectin group. So then we wanted to understand that extra gain, what the value of the gain was. So we looked at the time of making the presentation what the average sell price for a 600 to 700 pound calf in the US was, and it was $252.75 per hundredweight. We then converted that to dollars per kilogram. So to get a value of gain per head, we multiplied the value of gain per head on a kilogram basis times that $5.57 per kilogram to get a value of gain for Valcor of $423.82. Compare that to $400.26 for ivermectin, which gave an advantage of $23.56 on value of gain for Valcor over doramectin. We also wanted to bring in the cost of treatment. So to quantify that, we just looked at the retail cost of both of the products on the online Valley Vet website and converted that based off the day 0 body weight and the list price to a cost per mil and then a total cost of treatment per head. So for Valcor, it cost $3.92 compared to only 85 cents in the ivermectin treated group, which gave a $3.07 premium. So then to calculate the net value of gain per head, we subtracted the cost of treatment per head from the value of gain to get the net value gain per head of $419.90 for Valcor compared to $399.41 for ivermectin, which gave an increased net value of gain per head for Valcor over doramectin of $20.50 per head. So in summary, the doramectin levamisole combination product, Valcor, significantly improved efficacy against gastrointestinal nematodes by reducing fecal egg counts by 99.9% compared to only 85% in the ivermectin treated group, indicating a potential presence of macrocyclic lactone-resistant gastrointestinal nematodes in this particular population. And because of that increased efficacy, we saw an improved performance from an average daily gain and total weight gain perspective over the 56-day study. And then if we take that a step further and look at it from an economic standpoint, a net value rate of return of $20.50 advantage of using Valcor over doramectin. If we extrapolate that over the population of the study, we enrolled 1,548 head. If you extrapolate that net value, it's about $32,000. The new doramectin levamisole combination endectocide Valcor can be an effective tool and economically attractive endectocide alternative for cattle producers and veterinarians facing macrocyclic lactone resistance. Thank you for your time.
Thank you very much. We have room for a couple of questions before going on a break. Go ahead, please.
I have a question for you that you compared it with ivermectin.
Yes, sir.
Do you think the results will be different if you had a levamisole comparison? Because it's a combination, right? You used one of them, but levamisole is the other part of the combination, so.
No, that's a good question. So the question, I don't know if everybody heard it, was what would the difference have been if we would have saw just using a levamisole? The reason that we used the ivermectin was it's most prevalent. It's one of the most prevalent used over-the-counter anthelmintic in the U.S. And that's what our producers were interested in seeing, the comparison. And so, and levamisole is not used in the U.S. very much. So we felt it was a better comparison to compare it to ivermectin.
Thank you.
Another question? Go ahead, please, doctor.
Thank you for your presentation. It was very clear. And I would like to ask you, what do you think the combination between doramectin and levamisole, there is a synergist effect or additive effect? Or, as it was mentioned, levamisole is working well in your trials?
So the question was whether it was a synergistic or additive effect of levamisole. I think we would consider it to be an additive effect, right? In our dose confirmation studies, we compared it to doramectin alone, right? We brought in levamisole on top of that in the combination, and we saw improved efficacy against multiple genuses of gastrointestinal nematodes. So I would consider it an additive effect.
Thank you very much. Another question? We have room for one more. Okay, so we thank you very much for the conference. So with no more questions, we thank Dr. Jase Ball. And we're going to go to a break right now, 30 minutes break in the exhibit hall. We'll be returning on 11 with a keynote lecture of Cryptosporidiosis. So see you in about 30 minutes. Thank you very much. Welcome back, everybody. So it's my honor to present to you the next keynote lecture with Dr. Luis Miguel Ortega-Mora with the theme Cryptosporidiosis in cattle and recent advances in prevention. It is important to mention that Dr. Luis gained the Premio Extraordinario de la Licenciatura, PhD cum laude, Diplomat of Facto by the EVPC, full professor at the Animal Health Department of the Complutense University of Madrid, director of the Solvet Research Group, CEO of the spin-off Solvet Innova. Main scientific interest concerns the pathogenesis, diagnosis, and drug and vaccine development of protozoan diseases affecting ruminants. He has published more than 300 SCI research articles and supervised over 25 PhD students. He is author of 8 patents. He was the president of the scientific committee and member of the national board of the Spanish Association of Cattle Practitioners from 2008 to 2016. Former coordinator of the Spanish National Research Program in the area of livestock, aquaculture, and fisheries at the Spanish Ministry of Science and Innovation, and former member of the Scientific Advisory Committee of CERESA. From 2013 to 15, was national expert in the Horizon 2020 Europe program. Doctor, welcome.
So thank you very much for the introduction. Good morning, ladies and gentlemen. It's a great pleasure to be here today. Before I start with my presentation, I would like to thank the meeting organizers and also the sponsors, MSD, for their kind invitation to be here today. My presentation is going to deal with cryptosporidiosis in calves. This is a subject that I consider very, very interesting. And what I'm going to try to do is to review some of the main points in this disease, and also try to bring here today some of the new tools that we have for control this relevant parasitosis. Before I start with my presentation, I would like to make a short introduction about the relevance of mortality and morbidity in calves. This is something that I think is associated to the relevance of cryptosporidiosis in cattle. This is a very, I would say, important study that was developed a few years ago by the USDA, just looking for the main causes of mortality and morbidity in dairy calves. In this study, they point out that mortality was around 5% during this period in pre-weaned calves, and morbidity around 33%. Mortality was more or less on the objective of the program, but morbidity was 8 points above the objective of the program. As you can see here, in mortality, the main cause of losses are the digestive diseases, and this is also happening when we look for the cause of morbidities in dairy calves. Digestive are around 50% of the causes of morbidity in this group of animals. When we look to other relevant aspects, as for instance treatments, we can say that these diseases in this group of animals are treated mainly by antibiotics, is the main group of drugs that they are used, and also they detected some factors that could be associated with morbidity in calves. You can see that birth weight and serum IgG status were two of the main aspects related with this morbidity. In addition, I think that it's important to mention that we should keep in mind that some of these infectious agents that are causing this mortality and morbidity, they are zoonotic. I mean, they can cause disease in humans, and Cryptosporidium is one of the main examples. This is another study related with morbidity and mortality, mainly in calves, in this case in the UK. And as you can see, we can see the accumulated mortality rates in dairy and non-dairy calves, and there are huge differences in mortality rates between dairy and non-dairy calves, and also between males and females. And this is clearly associated with management factors in these animals. We have been talking about mortality and morbidity, and now we are going to move to the digestive diseases, and the neonatal calf diarrhea syndrome is one of the main causes of mortality and morbidity in pregnant calves. In this study coming from the same country, the UK, we can see that when they were looking for the different agents participating and diagnosed in this group of animals, you can see that Cryptosporidium alone or combined with other infectious agents were responsible of around 50% of the diagnoses that were made in these animals at that time. Similar results we can see in other papers that has been published in different countries, for instance, in Spain, in dairy calves, when they were looking for and detecting agents causing diarrhea in dairy calves. You can see that, again, Cryptosporidium was the main parasite that was diagnosed, the main agent that was diagnosed in these animals, alone again or in combination with other agents, either viruses or bacteria. And if we move to other continent, Asia, in this case China, we are going to get more or less similar numbers. And as you can see here, around 50% of the calves with diarrhea, Cryptosporidium is detected in these animals. So the main message coming out from this part of my presentation is that Cryptosporidium is one of the main agents that is involved in the neonatal calf diarrhea syndrome in pregnant calves, either in dairy calves or in beef calves. Clearly, there is an association, there is an age-related presentation of these agents causing neonatal diarrhea. And as you can see, Cryptosporidium start to be present in the farm around the first half of the first week of birth, and then is going to be present mainly to the second week of life of the animal, and finally, the final cases are present in the third week of life of the animals. Just a short history of the evolution of the knowledge on Cryptosporidiosis. Cryptosporidiosis or Cryptosporidium, the agent, was described early in the 20th century by Ernest Teicher. Ernest Teicher was a physician, was a parasitologist and a pathologist, and at that time he described mainly using a microscope the parasite and also the life cycle of Cryptosporidium. But we need to wait until the decade of the 70s in the 20th century to see that Cryptosporidium was associated at that time with bovine diarrhea, and more or less at the same time, Cryptosporidium was reported in humans. In the decade of the 80s, the role of Cryptosporidium as a primary pathogen in ruminants was confirmed, and also the parasite presence was detected in AIDS patients. You may remember that HIV infection at that time was very relevant in humans, And also, at that time, the first water-associated outbreaks were reported. In the decade of the 90s, probably the most important point was the largest reported waterborne outbreak associated to Cryptosporidiosis. More than 400,000 people were involved in this outbreak, and that happened in Milwaukee, in the US. And finally, in the last 20 years, there has been an increase in the knowledge of the disease. More than 30 species of Cryptosporidium has been described. Also, several PCR tools, several drugs, they have been used in the field now, and they are commercialized, and they are available to treat the disease. And the final point that I would like to mention, and I think this is relevant, is the first commercial vaccine in ruminants has been approved. The three main points that I'm going to deal with during my presentation are the following. The first one is I'm going to review some of the biology of the parasite and the main points associated to disease transmission. The second point in my presentation is going to be the description of the infection dynamics, the clinical signs, and the impact of the disease. And finally, I'm going to tackle some points related with diagnosis and the control measures for this disease. Let's start from the beginning. This is a study developed by Pablo Diaz and co-workers in the northwest part of Spain. And in this study, they were testing cattle during their life. And as you can see here, the prevalence of Cryptosporidium was higher in the group of animals between birth and the first month of life. But what is more important, they were detecting and genotyping the species that were associated with this infection. And the more frequent species in cattle, and this is also described in several other words, are C. parvum, C. bovis, C. ryanae, and C. andersoni. But the important point for us is that only Cryptosporidium parvum is associated to the neonatal diarrhea in calves. And this is the most important point. And in addition to that, Cryptosporidium parvum is the zoonotic species associated with transmission from ruminants to humans. And this is the message that I would like to bring here today. Only C. parvum is associated with neonatal diarrhea in cattle. And as you can see, C. parvum is predominant during the first month of life, but it's also present in other age groups, and again, could be present in animals higher than 2 years of life. And this is also important. I would like just that you keep in mind this point, because that could be associated with the shedding of oocysts by asymptomatic carriers. Some data about the prevalence of crypto infection. There was a meta-analysis and a systematic review that was done a few years ago, last year by Chen and co-workers, 2023. And in this meta-analysis, they established that the prevalence in dairy cattle worldwide, in the different papers that they have reviewed, was around 22%. The prevalence was slightly higher in pre-weaned calves infected, was around 25%. And again, the prevalence was again higher in diarrheic calves. Another important point is that the most prevalent subtype worldwide was this 2A genotype, that is a zoonotic genotype, and this is also important from the One Health point of view. Some other recent words concerning prevalence of the disease. Here is a comparison between the work that was done by Uri and co-workers and also by Pinto and co-workers, the first one in the US, the second one in the EU. Here you can see that the number of positive farms in the US was around 94%. 43% of the animals, pre-weaned calves in this case, were infected. And in Western Europe, the work by Pinto and co-workers established that 93% of the farms in the study were infected, and the prevalence in the 3 different countries that were involved, France, Belgium, and the Netherlands, was around, you can see here, between 20 and 25%. Let's remember some important points about the biology of the parasite. And here we can see that Cryptosporidium is a coccidia. I mean, there is going to be a resistant phase in the environment, that is the oocyst. And in addition to that, it's an intracellular parasite. The target cell is going to be the enterocytes in the host. Here you can see in this picture how the parasite is colonizing. This is a villi in the intestine, and is colonizing the apical part of the enterocytes. All these small dots are parasite stages that are proliferating in the enterocytes. If we escalate the image, we can see here the parasite stages that are in this particular location that is described as intracellular but extracytoplasmatic. And as you can see between the parasite stage that is allocated in a parasitophorous back wall and the cytoplasm of the host cell is this feeder organelle that, and the feeder organelle, the mission is just to establish the nutrition and also other components that are going to take from the parasite to from the cytoplasm of the host cell. In this picture, we can see very clearly the feeder organelle, but also you can see one of the points that is going to be very important from the pathogenic point of view is the atrophy of the microvilli of the enterocytes in the places where the parasite is proliferating. What about the parasite cycle? Just two relevant points that could be relevant for the pathogeny and also the clinical signs associated to the disease. The animals are going to be infected by the ingestion of these thick wall oocysts that are in the environment, contaminating the feed, contaminating the water, contaminating the environment. And in the intestine of the animal, the parasite is going to exist and is going to invade the host cell, the enterocytes. Here, 2 cycles of asexual multiplications are going to take place. And finally, a cycle of sexual multiplication is going to give place to the sporulated oocysts. And one important point is that all this cycle could take place very fastly. I mean, in 2-3 days could be complete. This is one important point. And as you can see here, the prepatent period between infection and the moment that we are going to be able to see these oocysts in the feces of the animal could be as shorter as 3 days. Another important point is that the oocyst excretion, oocyst shedding, is going to last for a period that is going to be between 1 to 2 weeks. And that is going to depend, again, from the host immunity and also the ability and the vitality of the animals to develop a good immune response against the parasite. In this cycle, I want to point out one relevant point, and is that there is the possibility for this cycle to continue along the time, because there are 2 autoinfective stages. The first one is the merozoite 1 here, and the other one are these thin wall oocysts that can recycle this cycle along the time until the immune response of the host is able to cut this cycle. Some factors that could be associated to disease transmission. Some of them are clearly associated to the parasite, and as you can see here, one important point is that the infected animals, they can shed enormous amount of oocysts with feces, more than 10 to the 10 oocysts during this patent period that we have described that could last for 1 to 2 weeks. The other important point is that the oocysts are immediately infective after being excreted. And in combination with that, the low infective dose that is necessary to initiate one infection in one animal. How you can see here is isolate dependent, but it's going to be between the 9 oocysts for this isolate to around 1,000 oocysts for this other. Very low dose in any case. In addition to that, we need to know that the oocysts are very resistant in the environment. They can resist between temperatures between 4 to 60 degrees without any problem. They can survive in the silage, for instance, and also they are resistant to several treatments that we use to potabilize water as chlorine. So they are extremely resistant for the environmental conditions, but also to several disinfectants. Looking for the host factors, we can see that, and we have already mentioned this point, the clinical disease is going to take place in pre-weaned calves, mainly in animals that they have less than 4 weeks of age. Animals with more than 6 weeks could be infected, but they are going to be asymptomatic. There is clearly an age-related resistance associated to the infection. Adult cattle can be carriers. They are going to be able to shed a small amount of oocysts. And there is an absence of fully protective adaptive immune response. I mean, the animal could be reinfected in the future, although they have experienced a primo infection in the past. Clearly associated with this host factor are the vitality of the animal and also the colostrum intake and the management of the animal during this period. Finally, related with the environment, we can say that, of course, the infection is associated to the presence of the oocysts in the contaminated water, food supply, and also the oocysts can be disseminated via insect vectors. There is a seasonal increase in prevalence that has been associated with humidity, probably associated with the fact that the oocysts can survive for longer periods with the environment is going to be humid. And the prevalence is going to be lower when we have concrete, for instance, on when we use very basic measures at soap, detergents, and also frequency of cleaning. And finally, the prevalence is going to be higher when we increase the density of the animals or when the soils are poorly drained. Coming to the second part of my presentation, the infection dynamics. In this graph, it is represented very clearly how is the presentation of the disease in a farm. As you can see here, the animals start to be infected and then showing diarrhea very early in life. I mean, day 4, day 3 of life, they can start to show diarrhea and they start to shed oocysts, but the infection is going to experience a peak in the 2nd week of life. And this is a constant picture that we can see in every farm when we have a Cryptosporidiosis infection going on. This is a work that we did many years ago. What we did was infected animals at different age of life. And in this, the red bar is the group 1, where animals infected very early in life, 3 days of age. The second group were animals infected at 20 days of age. And the final group, group 3, were infected when they were around 2 months of age. And as you can see here, there is clearly very different picture in this group of animals, because only the group that was infected very early in life is so a patent period that was very prolonged in time, and also they were able to shed enormous amount of oocysts during this period of time that was between 2 to 3 weeks of patency. But the animals that were infected they were 1 month old or 2 months, they said less oocysts in general, and the group that were infected at 2 months of age, I mean, it was very difficult to detect this amount of oocysts that, as you can see, comparing with the scale, was very low. This is the image that we are going to get in the gut of an infected animal. This is an histologic picture with the typical parasite proliferating in the villi, but this is an electron microscopy picture, and all these bubbles, they are parasite stages that are proliferating in the gut. As you can see here, as the cause of this proliferation of the parasite, what we are going to see is an atrophy of the villi, and also we are going to see that all the enterocytes that are mature enterocytes, where the parasite is proliferating, are going to be lost, and these cells are going to be replaced by some immature cells, enterocytes that are less mature from the physiological point of view, and they are coming out from the crypts or Leverkuhn, that they are here in the base of the villi. The other important point, this is the second part of the work that I was presenting before. All the animals that they were infected when they were very young are going to experience a clear diarrhea. Here you can see the decrease in the fecal solids in this group of animals, in group 1, was very pronounced, compared with the decrease in fecal solids in the group infected at 1 month or 2 months of ages. And again, the number of animals that they experienced diarrhea was very clear in the group that were infected very early in life, but not in the others. I mean, that was the original description where we initiate this theory that all the animals that they are infected very early in life is going to experience cryptosporidiosis from a clinical point of view. The other important point that I would like to mention in this part of my presentation is that now we have several studies where they have initiated to explore the alteration in the microbiome of these animals that they are infected by C. parvum. And now we have several reports in the literature when we can see in these reports that after Cryptosporidium parvum infection is installed in one animal, there is a pronounced dysbiosis in the animals. A high prevalence of Clostridium, for instance, has been observed. Also, several groups of bacteria, as Fusobacterium, also were very abundant, and that was associated with an increase in the oocyst output and in the diarrhea. In conclusion, what we can observe is a decrease in the microbial diversity of this group of animals and an increase in susceptibility. And this is similar to the things that they have observed in other enteropathogens, that they are causing neonatal diarrhea in calves as rotavirus, where you can see that some of the groups are clearly modified when we compare healthy animals with rotavirus-infected animals. In conclusion for this part, I mean, there are short-term effects, there are some medium to long-term effects of the disease. One of them, and this is important, is mortality, but we have to say that if there are not co-infections, if there are not a bad management of the animals during this period, mortality is going to be low, but morbidity is going to be high. And as you can see, several studies are reporting the effect, for instance, in less weight in beef heifers at 6 months of age. This study was done in the UK. Also, association with other diseases as pneumonia, and treatment increases also in these animals of around 25%. But also, very recently, there are several works in the literature that they are reporting a negative impact in milk production and also loss of genetic merit, and these are clearly long-term effects on this neonatal diarrhea experiencing very early in life for these animals. The final point in this part is that we need to consider that C. parvum is a zoonotic parasite. Here are the 19 species, Cryptosporidium species, that they have been described in humans. It's as you can see, a long list. Cryptosporidium hominis, that is the parasite that is anthropogenic. I mean, is the parasite that is associated to human, is the more reported Cryptosporidium species. But second in this list is Cryptosporidium parvum, that is clearly associated as main reservoir with ruminants. The final part of my presentation, I'm going to deal with diagnosis and control. For diagnosis, we have been able to see that the animals, when they are infected, they are going to excrete, they are going to shed huge amount of oocysts during the patent period. This is a table that I have copied this table for the terrestrial manual of the OIE, is the 2022 manual. And as you can see, we can see here the purpose of the infection, confirmation of clinical cases or prevalence of infection when we are doing, for instance, surveillance or epidemiological studies. There are several techniques that they have been described, and we can use this technique to detect the oocysts in the feces of the infected animals. The first group is the conventional microscopy associated to the different stainings, negative staining, that one, that is Heine technique, or this technique that is a modified Thiel-Nielsen. As you can see, the oocysts are detected in this case in red color. When we are trying to confirm clinical cases, this conventional microscopy is very useful. As you can see, 3 crosses. So if we only have this purpose, we can use this kind of technique without any problems. Also, we can use immunofluorescence. As you can see here, the oocysts are going to be associated to this green color. And again, this technique are also useful for confirmation of clinical cases, but also when we are doing surveillance. What about immunochromatography? Immunochromatography is very popular, but the problem is that, at least in the literature, it has been described several false positive associated to immunochromatography. And this is one point that we should keep in consideration when we are using these kind of techniques. And of course, as a point of care technique, it's very useful because we can obtain an immediate result very quickly. But the point that we should keep in mind is not only the false positive, but it's also the low sensitivity of some of these immunochromatographic techniques. Finally, the ELISA techniques are very useful, as you can see in the OIE manual 3 crosses for both type of approach in diagnosis. And finally, one comment about PCR techniques. PCR techniques are the more expensive, of course, and this is something that we should keep in consideration. But the advantage of using PCR is that they are very sensitive, they are very specific, and also we can genotype the isolate that is circulating in a concrete farm. And this is something that we should keep in mind if we want to use PCR. In addition to that, some quantitative PCR techniques has been described, so we can quantify the amount of oocysts that are shed by this animal, if this is something that we consider of use in our case. Again, when we want to choose the technique that we are going to use, we should keep in mind that if we are testing animals in that part of the patent period, any technique probably is going to work very well. But if we are going to use the technique at the final point of the patent period or at the initial points of the patent period, I mean, we need to look for techniques that could be more sensitive. And in the case that we are testing adult animals, in that case, the amount of oocysts that they are going to be shedding, you can see here the scale, are going to be very, very low. So in that case, we need to concentrate the oocysts before do the detection technique. And as detection technique, we should go for techniques that are really, really sensitive, immunofluorescence, for instance, or PCR as an alternative. The final point of my presentation is about control measures, and this is something that is, of course, very important. We have seen the risk factors that are associated to infection, the biosafety measures, and the risk factors. Avoid these risk factors is going to be very, very important. Also, the transfer of colostrum is going to be a very relevant point. And I'm going to comment several other points where I'm going to do some extra points. The first point is about the use of disinfectants. And this is something that when one is dealing, I mean, a veterinarian is dealing with a crypto outbreak, we want to know what could be the disinfectant that is going to work better. One thing that I would like to mention is that the oocysts are sensitive to the temperature, very high temperatures, higher than 60 degrees centigrade, for instance. They are very sensitive to desiccation, and this is a practical measure. If we can keep an area desiccated for a while, most of the oocysts are going to lose viability, they are going to lose infectivity, and this is a very practical and with low-cost measure. And again, the impact of sunlight also could be very good to sterilize an area. So these are very practical things that you should keep in mind. Coming back to the disinfectants, I mean, the effect is going to be associated to the concentration and the time that the parasite is exposed to the disinfectants. One important point is that there are not a lot of papers in the scientific literature when they have used experimental models to test and also to explore the viability of the oocysts after applying the chemical disinfection. The number of reports that they have used these, for instance, animal models to explore infectivity of the oocysts is not very high. So there are two groups, just to summarize, that could be used as they have been shown to be effective against oocysts. One of them is ammonia. As you can see here, the dilution is 1 to 2, 1 to 5. And the problem is that the disinfectant should be in contact with the oocysts for a very long period, 18 hours. So in addition to that, the ammonia should not be used in a confined space because it has an irritant effect. The other group of disinfectants that it has been shown to be effective against oocysts and the hydrogen peroxide. They can be effective in very short period of time, 20 minutes. The problem is that could be caustic and corrosive. And also the problem with hydrogen peroxide is that it's going to be inactivated in the presence of organic material. So depending on the conditions of the farm, we can choose one group, the other, or combine both groups of disinfectants. The second point is the use of drugs against the diarrhea caused by C. parvum in calves. In Europe, we have two groups of drugs that they have been used, and they are approved by EMA, the allofuginol lactate and also paromomycin sulfate. In the case of the spectrum of the allofuginol, as you can see, there is a huge antiprotozoal effect. In the case of paromomycin, it has a broad spectrum with bactericidal and antiprotozoal effect. Halofuginone has been approved in most European countries. Paromomycin is approved in a few countries in Europe. The posology is that one. Additional therapeutic usage in the case of halofuginone is not any additional use. In the case of paromomycin, it could be applied for treatment of E. coli strain susceptible to paromomycin. The effect of the first group in the microbiota is expected to be low. The effect of the second group, or the paromomycin, is expected to be high, although there are not results confirming this stream. This is something that I should mention. Concerning toxicity, both drugs, they have some side effects that we should keep in consideration, and also we should keep in consideration the withdrawal period for IMID, for halofuginone, and also for the paromomycin sulfate. There are going to be some other words in this session reporting the use of paromomycin. Probably this is going to complement what I'm summarizing here. Another point is the use of prebiotics or probiotics. And I have included this work here, this paper here, when they have investigated the use of several probiotics for using against neonatal diarrhea. In the case of Cryptosporidium, the statistical results that they obtained show that there was not effect in the occurrence of Clostridium, for instance, or Cryptosporidium parvum, or levels of Campylobacter. And what they are suggesting, and I think is very interesting, is that it's very difficult to prove the efficacy of these probiotics. So the model should be established very strictly, I have to say, because there are a lot of environmental factors that could have influence, and this is something that we should keep in mind. I mean, the efficacy should be done in very well-controlled field trials. The final point of my presentation is about the use of vaccines. And what is the perfect vaccine in the case of Cryptosporidium? I mean, the vaccine is going to be based in the production of antibodies that is going to be transferred from the dam to the newborn calf through colostrum, and the level of these antibodies in colostrum is going to allow that the parasite is not going to multiplicate. That is going to be the base of this kind of vaccines. An ideal vaccine is going to have a target that probably has to be shared with several parasite stages that could be infecting the enterocyte. And it has been shown in the literature that these proteins are mainly glycoproteins that are associated to the invasion and proliferation of the parasite in the initial stages. So some of these candidates, we know that they have been reported previously in the last 20 years, and mainly, as I have mentioned, are glycoproteins that are shared between these parasite stages. There are at least 3 of these proteins that they have been tested in ruminant models, GP40, CP15, and P23, that they have the requirements that they have already mentioned. They are shared by different parasite stages and could be used as target because they are relevant proteins in the invasion and proliferation parts of the life cycle of Cryptosporidium. Very recently, it has been reported the identification of one of these glycoproteins, that is GP40, but also monoclonal antibodies has been developed against this glycoprotein. And as you can see here, these monoclonal antibodies against GP40 are shared between different parasite stages in the life cycle. Finally, a vaccine has been produced using this GP40. This protein has been expressed in baculovirus. You may remember that this is an eukaryote system that is expressed in XS cells, and this is going to allow to keep the conformation of the protein, and this is very relevant for glycoproteins, to keep the original conformation. The vaccine has been applied during the dry period in the dam, and the colostrum that was obtained for these animals, and that has been reported very recently in this manuscript. You can see here the level of IgGs against GP40, this relevant protein in the control group and in the vaccinated group. As you can see, there are huge amounts of these antibodies in this case. And the most important point is when this colostrum was supplied to a group of animals that were feeding with replacer, with milk replacers, or that they were feeding from the animal, they were milking from the animals, what we can see is that there was a high decrease in the diarrhea when we compare the group of the animals that we were taking this colostrum from vaccinated animals compared with the group of animals that they don't receive this colostrum from vaccinated animals. And that took place also in the group of animals that they were fed with the milk replacer and with the group of animals that they were fed with from the dam. So this is a very important point. This is a proof of concept that this vaccine could work in the field, and this is something that could be used as another tool in the future, together with the other measures that we have shown in our scheme, trying to control the diarrhea caused by Cryptosporidium. This is the final part of my presentation. I have tried to summarize during my presentation some relevant points in the infection, and also I have tried to review some points important about diagnosis and control measures. So finally, I would like to thank you for your attention. This is our contact, the Soluble Group in Madrid, also the spin-off that we have in our group. These are the funding sources and the collaborators that we have in our group, and thank you very much. Muchas gracias.
Thank you very much. Thank you very much, Dr. Ortega-Mora. So we will start now with the scientific conferences, beginning with Paula González-Rivas. Welcome, with the subject injectable trace minerals associated with vaccination against Haemonchus contortus, program to reduce worm egg counts and increase average daily gain in lambs in Australia. Welcome.
Good morning, everyone. My name is Paula González-Rivas. I am the Technical Services Manager for Livestock Nutrition at Vervac, Australia. I'm very glad to present today one of the latest studies that we have conducted to look at the effects of injectable trace minerals in sheep.
Disculpen, pueden poner la presentación siguiente, por favor, y el tiempo. Gracias.
Sorry. All right. So that's the topic of the presentation. But first of all, we want to discuss a little bit about trace minerals, immune responses to vaccination, and parasite control in sheep. Trace minerals, copper, selenium, zinc, and manganese, are very important for the immune system. They're important to maintain the integrity of the gastrointestinal tract, the respiratory tract, also the genital tract, skin, mucous membranes, etc. They are very important for the not specific or innate immune responses to mount inflammatory immune responses against any impact from the environment, injuries, etc. Trace minerals are also very important for the specific or adaptive immune responses and the production of antibodies. The relationship between trace mineral nutrition and parasite control is clearly not well understood, of how good nutrition and good trace mineral nutrition leads to low burden of parasites and increased host resistance to the parasites. For example, oral zinc supplementation results in low levels of parasite infections in cattle and sheep. Manganese supplementation is highly correlated with low worm egg count in sheep. Higher worm egg counts are seen in animals deficient in cobalt and therefore vitamin B12. Copper oxide wire is a way of supplement copper, has been associated with reduction in abomasal nematode population of worms in sheep, but with no effect on the establishment of the intestinal population of worms. Under experimental conditions, dietary molybdenum can reduce the establishment of abomasal nematode population, but not the pathogenicity in lambs. Therefore, it's unclear whether nutrition of trace minerals create a direct effect of the gastrointestinal tract of cattle and sheep, or is associated to immune responses. One of the ways to supplement trace minerals can be oral supplementation, relying on what is in the pasture, for example, and also injectable trace minerals. Injectable trace minerals have been in the Australian market for more than 15 years. These allow to deliver a specific amount of trace minerals, bypass the antagonist interactions of trace minerals with feed particles and other elements in the rumen, therefore improving the absorption and utilization of these elements, overcome the variability associated with fluctuations in voluntary intake of oral mineral mixes, and complement oral supplementation. Indeed, the best results of studies conducted with injectable trace minerals are being in animals well supplemented with trace minerals in an oral supplementation, meeting or exceeded nutritional recommendations. Injectable trace minerals have been demonstrated to improve the trace mineral status, supporting challenging events of the life cycle of livestock by enhancing the antioxidant system, immunity, and fertility. Several studies have shown the benefits of associating injectable trace minerals with vaccination program. These are the results of the earliest studies that demonstrate that when an animal receives a vaccine, there is, within the first 15 days after vaccination, there is a reduction on the levels of trace minerals in the system: zinc, manganese, copper, and selenium. However, when animals receive injectable trace minerals at the same time as the vaccine program, this supplementation helps to increase or reduce the reduction of trace minerals in the system. And this has been highly associated with improved vaccine responses in terms of antibody production. This has been demonstrated in cattle using vaccination programs against bovine respiratory diseases, for example, pestivirus and IVR. So calves receiving injectable trace minerals at the same time as a vaccination had greater neutralizing antibody titers to herpes virus 14, 30, and 60 days after vaccination compared to control animals. And other studies, they show similar results, showing improved vaccination responses against pestivirus 14 days after vaccination. This suggests that humoral immunity can be enhanced by injectable trace minerals. This is the summary of another study that shows that animals that receive injectable trace minerals at the same time as a vaccination against bovine respiratory diseases produces the antibodies sooner than control animals at day 28, with more animals reaching protective antibody levels compared to control animals. Let's move to the worms. Barber's ball worm, Haemonchus contortus, or in Spanish, palo de barbero, is a blood-sucking parasite that affects sheep and goats, producing alteration in the blood, so it produces anemia resulting in death, and also produces changes in biochemical, immune markers, resulting in oxidative stress. This is seen as a reduction in the activity of superoxide dismutase enzymes and an increase in markers of peroxidative lipid changes. Also, serum zinc and copper levels are significantly low in infested animals with various levels of infections, light or moderate or heavy. So this can be due to a large utilization of trace minerals to support the immune responses of the host to the parasite, and also changes in the gastrointestinal tract to the damage of the lining of the gastrointestinal tract, reducing the absorption of these trace minerals, and also associated with low feed intake. Barber's ball worm reduces significantly the serum immunoglobulins, IgM and IgG, limiting the immunoglobulin release into the abomasum, reducing the protection to the worm. The immunity in sheep is achieved by day 18 or 24 months old, so it's very late. It takes quite a long time for the animals to become resistant to the parasite. Lambs under 6 months of age are not able to mount the effective immune responses to the parasite, and those are the most affected in the flock, due to a delayed development of acquired immunity to the parasite. In Australia, there is a widespread parasite resistance to Barber's ball worm, with fairly no single active working against the parasite. And currently, the only way we have to control the parasite is using triple actives. And this is a parasite control that we need to be very careful, not overutilize that. So therefore, one of the options that is in the Australian market is the vaccination against Haemonchus contortus. This is a vaccine that is effective to treat and prevent Barber's ball worm, and is currently available in Australia, New Zealand, South Africa, and in the UK. Like all vaccines, it stimulates the natural immune responses of the animals. The antibodies circulate the blood, and the parasite ingests these antibodies with the blood meal. The antibodies then attach to the lining of the Barber's ball intestine, blocking the digestion and starving the worm so that it produces fewer eggs and finally dies. So at Virbac, we know that this product is available. It's from another company, but we have injectable trace minerals. We know the story of the injectable trace minerals improving vaccine responses, and we wonder, we will see the same responses using a vaccine against parasites? So that's why we have the following hypothesis. If we associate injectable trace minerals with a Haemonchus contortus vaccination program, can we reduce the worm egg counts of Haemonchus beyond to what is expected with the vaccine alone? So this is why we ran this pilot study in Australia in 2021 and 2022. So we included 60 crossbred lambs that received the vaccination protocol from Markin. So this consists in up to 6 vaccines separated between 3 to 4 weeks. And the lambs receive a parasite control at weaning to control scour worms as well as early Barber's ball worms. The lambs also receive a clostridial vaccination at marking and also a booster at weaning. The lambs were moved to a prepared low worm risk paddock where sheep had not been grazed for 3 months. So this is the standard protocol for the vaccination program to make it work, and we try to apply the same for these lambs. The difference is that half of the lambs receive 2 injectable trace mineral doses every 3 months. Here we use a product we have in Australia called Multimin Copper Free that contains selenium, manganese, and selenium, manganese, and zinc. So they receive these injectable trace minerals at weaning and then 3 months later. Body weight and average daily gain was collected every 14 days from marking. Individual worm egg count and larval culture were collected by fecal samples every 14 days from weaning, and the efficacy of the treatment, which is the injectable trace minerals plus the vaccine, was calculated as per this equation. So this is the timeline of the experiment. It lasted for 181 days. Animals received the first vaccine against Barbes-Pol at marking, and then they received the first injectable trace mineral at weaning, along with worm egg counts every 14 days and measures of weight gain as well. On the results, we saw very high counts of Barbes-Pol and black scabbard worms. That was pretty unusual, although not unexpected, because this farm has very severe resistance to these parasites. We expected that the weaning range applied, weaning parasiticide applied at day 45 will bring the fecal egg count to 0, but these parasiticides didn't work, and we had to intervene at day 75 using a salvage range that consisted in triple and dual active parasiticides. This was on an animal welfare base, otherwise we will start losing the lambs. So as you see in the table, the counts are very high for in overall worm egg counts, and the percentage of Haemonchus and Trigestrongylus are very, very high too. In terms of the results of the efficacy of the treatment, we saw a higher efficacy at day 73, 110, and 136, which means that animals that received the injectable trace minerals at the same time of the vaccination program, they saw benefits by having lower counts of Haemonchus contortus in the feces. As I repeat, this is a pilot study. We try to evaluate by having minimum impact on the lambs by only collecting feces at this point. So you can see here the program of parasiticide that we have. The first winning program was using Derquantel and ivermectin. The salvage range contained tridectin, which is a bareback product containing moxidectin, levamisole, and albendazole. And then we had to add monopantel and ivermectin. The third parasiticide program contained Derquantel, ivermectin, and alpha-topos. Following with the results, this is the weight change of these animals. We saw benefits of using the combined program, injectable trace minerals, and the vaccination program by having the animals in the treatment group 1.72 kilos extra than animals in the control group. This also was shown with higher average daily gain for the injectable trace mineral group. So as a conclusion, we can say that the use of injectable trace mineral twice every 3 months from weaning alongside the vaccination program against Haemonchus contortus results in a reduction of the percentage of Haemonchus contortus eliminated in feces at certain time points, higher weight gain and average daily gain at 181 days compared to control animals. We can infer from these results that injectable trace minerals can increase the immune responses to Barbes-Pol vaccination. However, the drench resistance observed in this study may have hindered the weight gain. We could have expected better weight gain by controlling the worms using the vaccination and injectable trace minerals. So what are the next steps? Our further studies could help to understand what is the mechanism. Basically, we can see higher antibody responses to the vaccine, or we can see changes in oxidative status and antioxidant levels due to the injectable trace mineral injection, and also trace mineral levels and specific markers for Haemonchus contortus infestation. Thank you so much. I'm more than happy to answer any question.
Thank you very much, Dr. Paula. Thank you for sharing your research with us. I don't know if someone has a question for Dr. Paula. Apparently not. Thank you very much. It was very interesting. And now we welcome Dr. Damien Achard. Correct. Good. He's going to be talking about targeted selective treatments at housing with injectable eprinomectin in French dairy cattle using validated decision support system. Welcome and thank you very much.
Thank you for the kind invitation. Hello, everyone. My name is Damien Achard. I'm working for Siva Animal Health, and I will present a study we have done and the tool associated to try to refine the treatment of lactating dairy cattle with injectable eprinomectin. I think in Europe we just a little bit have not seen coming the resistance issue in anthelmintics, and it was not seen as a big topic there. Certainly as an exotic problem from South America, Australia, but things have drastically changed in the last 20 years. The first, I think, warning was clearly in the sheep sector in Europe, but then we had more and more evidence that cattle was also impacted by anthelmintic resistance. The newest data that have been published in Europe clearly linked the presence and pointed out the presence of resistance not only to old molecule but also to the macrocyclic lactones in cattle. So in face of this challenge, there is a different strategy that can be used. For sure, I think it's important to mitigate and to try to refine the use of anthelmintic, and that's really down to the diagnostic. We should be probably more focused to select the animal to be treated, so we have to answer simple questions again, such as who has to be treated, when they have to be treated, with what. We certainly have as many other tools we have to adjust to the local context. Is there any sheep breeding in parallel to cattle breeding, etc., etc. So the local context is absolutely essential to take into account. And certainly we have also to align what we are saying between the industry, the breeders, the veterinarian, in order to try to make a difference, because this is the situation we have today. Recently, well, not that recently, but maybe 15 to 20 years ago now, the refugia-based strategy has been implemented as a potential, not solution, but I would say mitigation of this problem of resistance. So the idea is quite simple, is to try to dilute the resistance parasites by sensitive parasites and leaving a certain proportion of animal and parasite unexposed to drugs, anthelmintic drugs. But when you turn that and try to think of the problem in lactating dairy cattle, what are the elements that can constitute the good answer to the problem? There is many parameters at farm level that can be used to document the level of infection of parasites and the data on farm. Parasitological evidence, so we can acquire data from the bull tank milk, from Ostertagi antibody level in the milk. That's something we can do. We can trace on younger animals the pepsinogen, but that's not of value for adult lactating dairy cattle. And we could eventually think of the fecal egg count excretion, but in cattle, this has proven to be of limited value as well. The farmer experiences another way also to try to select the animal to be treated based on his experience, and the experience of the farmer can be very broad, as you know. I mean, taking different direction and taking, I would say, different indication directly from the animals. That can be the aspect of the air, the general aspect of the animal, etc., etc. And there is also a third set of criteria which are simply the dairy cow's traits. So the milk yield, the parity, and the day in milk. That could be interesting. What we have done is an extensive study in France, so in grazed pasture-based herds. 120 grazing herds were recruited. So that's a considerable number of cows, as you can see, and we splitted the cows between those that receive anthelmintic treatment, here in instance injectable eprinomectin at housing, and a group that did not receive any anthelmintics. All those cows has, of course, to access to grazing, inclusion, or have a certain amount of inclusion of grass in the pasture. And the objective of the study was really to observe the variability in the post-treatment response on the milk yield, and to make difference at cow level, but also at herd level. The main conclusion at individual level was that we could clearly separate one set and one subpopulation of dairy cattle that responded favorably to and better to the injectable eprinomectin when done at housing, and that's the population of cow that of dairy cattle that you see on the top line, the blue, dark blue line. Those animals were less than 200 days in milk. That's the first thing, and they were also the one that started their lactation on the wrong foot. They were performing less well in comparison to their mates, and you see that during the 5 months after the beginning of the study, we have a positive and additive increase in the milk yield for this population of calf. So how do we really translate this research into practical, actionable items? And that's exactly the subject here, and it's the name of the program we have been developing in French, which is called TRI. It's an acronym for the rational and individualized treatment. And basically, it's trying to, I would say, come from the research, and in the end, coming with what we would need is the actionable list of animals to be treated. In terms of data collection, of course, everything was done with farmer consent, and data could and can originate from various sources, because nowadays there is a lot of way to acquire and to have this data. That could come from milk robot system. That could come also from the veterinarian herd program. That could come also directly from the farmer herd management software. And in other case, we could also have the data directly from the milk quality control bodies. So the first step, of course, is to refine the population within each herd to the animal that were less than 200 days in milk at the time of treatment, which, as I mentioned, was done at housing. And the second step was really to go further in the selection and to capture those dairy cattle that underperform at the beginning of their lactation. And here is a more clear view of what we mean by underperform. So the selection was done historically on the 81st days of lactation of each animal, And basically, of course, we could segregate animal by parity and in 3 tiers. So obviously, the first lower tier were the individual that perform less well than the 2 others, etc., etc. So which of the animal we select? Well, there is 2 levels that we can choose. Either a conservatory approach where we say, okay, only the animal that underperform and were classified as low within their class of parity are selected, and this is the only one that we will consider for treatment. And another, I would say, threshold is the secure sorting, and it's really a discussion with the farmer at which level he wants to adjust the threshold. And in this case, we would include also the medium performing animal into the selection of animal to be treated. What's the current use of the tool? So the tool is now have been launched in 2021 in France, only in France for the moment. It has, of course, started very well with the clinics that help us to perform the original trial that I mentioned before, but it has extended to other clinics. So the word of mouth had worked very well. And in terms of top reason for farmer to use the tool, there is 2 major ones. The first is really the return of investment that the farmers feel they have with this kind of tool. And the second point, which I think is worth mentioning, is the protection of environment. The benefit that can be described from this kind of tool is that it provides to both veterinarians and farmers an actionable tool to access directly to a list of cows to be treated, and those with the confidence that those animals will have the best potential to respond to treatment. Parallel and the consequences to this is a direct decrease in the amount of anthelmintic that is used, and in the summary and synthesis that we have since the beginning of this launch, there is a decrease by 60 to 75% of use of injectable eprinomectin. You see an example here on the right. Let's set up a dairy cattle, classical dairy cow farm in France with 85 to 90 lactating dairy cattle. Well, with the 3 sorting, and remember there is 2 levels and we can decide, but basically the farmer will end up treating 15 or maximum 22 animals out of these 87 lactating dairy cattle. That's just for the illustration. Future direction, we would like to push this tool a little bit further and try to integrate a way to measure the environmental impact of the use of anthelmintic, because again, this is a very important topic. So that's something we are considering. This so far is, I would not say manual, but we centralize the data and it's not automated at this moment of time, so this is something we are working on. And another extension we would like to make is to try to further extend this tool to other categories of animal, heifers, that's a first segment that we would like to extend to, and at other time of the deworming practices. So far this is a tool for housing, but we are considering to have also such a tool for different moments and practices, especially at turnout. So that's my conclusion for my talk. It's been a very exciting experience. I think it has proven also a great collaboration between the industry, scientific bodies, the vet and the farmer. And so far we have excellent feedback from everyone. I thank you for listening to my talk, and if you have any question, I will be glad to answer them.
Thank you very much, Dr. Ashar. Are there any questions regarding targeted selective treatments? Go ahead, please.
¿Me puede ayudar a traducir, doctora?
I'll try.
Gracias. Gracias, doctor, por la presentación muy interesante. En México tenemos una gran cantidad de ganado de pastoreo.
In Mexico,
que también
we have a lot of cattle on grazing systems.
Que también está en producción de leche. ¿Cree que podríamos trasladar este programa para estos hatos grandes, que son muchos animales? ¿Cree que sería práctico aplicarlo en hatos grandes, de gran tamaño?
Do you think it's an option to do the targeted selective treatment in big dairy production units in Mexico?
If they are graze-based or not graze-based?
Graze-based.
Graze-based. So basically how to extend this to a larger type of farm. Yeah, I understand. I think if your software and if you work with software and have a precise view of the different group of animal and have access to two simple data, the days in milk, also very important what I said about the performance when they really start their lactation. You can try to work with these two parameters from the data management herd that you have. These results, I think, are not always generalizable, so we have to take it into caution. This is really European-based, France-based. So I would probably do a first step of, I would say, trial, like a mini trial to see if this is the right criteria. If it is, then you can go on. If it's not, you will probably, and it's the most logical thing, you must probably adjust the response. But I think part of that could be used and useful.
Thank you.
Thank you very much.
Any other questions? I'll do my best to translate if there's someone that wants to ask a question in Spanish. No, if not, well, thank you, Dr. Ashar, for your conference. And we will continue with Dr. Geert Vertenten. So, good? Okay, good. He'll be talking about the effect of potassium sorbate on Crypto GP40 antibodies in colostrum. Welcome.
Thank you very much for the kind introduction and the good pronunciation of my name. So I'm Geert Vertenten, I'm Global Technical Director for Ruminant Vaccines in MSD Animal Health. Does somebody know potassium sorbate? No? This is not familiar, so I will explain it, no worries. And GP40? No? So I will explain that as well. It has been mentioned in one of the previous talks, but no worries. So, not to make too much secrets, I will start with my conclusion. So the addition of potassium sorbate had no negative effect on the amount of Cryptosporidium GP40 in antibodies in colostrum, and also potassium sorbate, and I will tell what it is an effective way to conserve colostrum at room temperature. So very often colostrum is harvested and collected, and they put it in the freezer for special conditions when you have poor colostrum to give to your young stock. But this is not always very practical. And that's why I was looking for different ways to conserve colostrum And one of them I found was potassium sorbate. And I think this may be more popular, as today it's mainly used in New Zealand, but I think it has many more possibilities. But first on GP40. Well, GP40 is glycoprotein 40, and it's one of a protective protein on Cryptosporidium parvum. And there's a new vaccine approved in the European Union from last year, and it will be commercialized in the next week or so in European Union, called Boviluscriptium. And it's the first vaccine that protects dairy and beef cattle against Cryptosporidium parvum. It's the same vaccine as another one you may know, Rotavirus corona. So it's a neonatal cough diarrhea vaccine. What we did, in fact, well, it took us, let's say, 23 years, so it's not that easy. But we had Rotavirus corona, we removed the antigens, and we made a new vaccine, and we put in GP40. So it's very similar how to use this vaccine. You vaccinate, primo-vaccination, your pregnant animals in the last trimester of the pregnancy, a few weeks before calving, and this stimulates antibodies against GP40. Those antibodies are transferred to the colostrum, and then if you give a proper colostrum to your newborns, this will help them to protect. GP40, well, here you have a nice picture of a sporozoite, so one of the stages of Cryptosporidium parvum. There are more than 100 antigens or epitopes on that parasite, or here the sporozoite, and we tested many of them, and they were non-protective. So if you would have antibodies and try to protect. But finally we found, and it's not a secret any longer, GP40, and this one has been defined as a protective antigen. This is a nice cycle here of Cryptosporidium parvum. I can explain it shortly, but it has been done in one of the previous talks. But you need at least, well, let's say around 17 oocysts to infect a calf in the first days of life. And this will, after a few days, give an excretion of 10 to the 10, so that's 10 billion oocysts in that individual animal. So it goes from a few oocysts to an enormous explosion, and it contaminates the environment, not only the calf itself, but all the calves that are around it. Even it's a zoonotic disease, so it can impact also people, mainly immunocompromised people, but also, let's say, children. And if you read literature, they say it's a mild diarrhea, but it's also, if I talk to patients, they say we need to stay at least 10 days very close to the toilet, which means 2 meters. I would not call this a really mild diarrhea. Anyway, we looked at the cycle, and there's an asexual and a sexual stage. I won't go in detail, but we, in a study, we looked if the antibodies against GP40 were attaching to several stages, and all the circles in red correspond with those stages. So they attach to, here, definitely the sporozoites, also trophozoites, mirons, and merozoites. So if you look in general, it attaches to 2/3 of the general cycle of Cryptosporidium parvum. But let's come back to potassium sorbate. So I'm sure you all have, in one day in your life, eaten potassium sorbate, because it's a food preservative, routinely used in food, in wine as well, but also in animal feed industry to inhibit bacterial growth. It's hard to find it really in a package labeled to conserve colostrum, as I will show here, but you can easily find it on the market. Even in some countries, in the supermarket, you can find potassium sorbate to just keep your food not contaminated. It has antimicrobial properties, so it stops growth and spreading of harmful bacteria. It inhibits bacterial growth in colostrum definitely, and in milk, and it also preserves antibody levels in colostrum. Here it's a link to one of those commercial products, but as I said, it may be not really dedicated to conserve colostrum. Also how you need to prepare it, because it's a kind of powder. You need to make a 50% solution, so you add 500 grams of potassium sorbate to 1 liter of clean water, and then you have, let's say, that 50% solution, and then you add it to 10 mLs to 1 liter of colostrum to make a 1% solution. And that colostrum can stay for many days, well, ideally still at 4 degrees Celsius, so in the fridge, but you can also put it at room temperature for a few days. But I look and I give some examples, I will show you some examples to illustrate what's possible, and then here specific with colostrum, looking at the GP40 antibodies. So the objective of this very straightforward and not very complex study, but that's easy, it's already late in the morning, so don't make it too complex. We will investigate, or we investigated, the impact of potassium sorbate on the stability and functionality of C-parvin GP40 antibodies in bovine colostrum, and that colostrum was obtained from the cows vaccinated with bovilis cryptium, or let's say the GP40 antigen vaccine. So you see the farmer here milking. Maybe that's not the way you do it, but it's a nice picture. Materials and methods. So we took frozen colostrum samples from one of the efficacy trials we've done for this Cryptosporidiosis vaccine. You can find it back. It's published here. There's also a poster available in the poster session this week on these trials. So it's really the colostrum we took from efficacy trials. We thawed it at 4 degrees day before use, so that it was nicely liquid at the time we mixed it with the potassium sorbate solution. So we did it again as I described in the previous slide. We made a 50% solution, and from that 50% solution we went to 0.5 potassium sorbate end concentration in the colostrum. So that's here. And so each sample was tested in 4 conditions. So at room temperature without potassium sorbate, so that's group A. At room temperature with potassium sorbate, so that's group B. And then a bit more ideal conditions is in the fridge. So 4 degrees with potassium sorbate is group C, and then 4 degrees without was group C, and with potassium sorbate is group D. We did it with the GP40 ELISA, which is an ELISA we developed at our own facilities in Boxmeer in the Netherlands. So it's an in-house test, very specific, of course, to support all kind of trials with our newly developed vaccine. We tested them on day 1, well, day 0, day 1, day 2, day 3, day 4, day 8, ideal 10. So 10 days in a row and frequent sampling. We did some statistics with the p-value of 0.05. So I have here a few figures, but I will guide you through it. So here's RT, if you can read it. So those graphs, they correspond with all the samples put at room temperature. And here it's 4 degrees Celsius, so those are put in the, let's say, the fridge. And you have a solid line, which corresponds with no potassium sorbate, and then you have the, let's say, the dotted line, it's potassium sorbate addition group. And why we have 3 lines? Because we split it up between samples that had low GP40 titers, so those 2 graphs, with mid titers, those 2 graphs, and with high titers are those 2. But mainly what you see is that the 2 lines are very close to each other. So it means that even the time, the temperature, or the, let's say, the addition of potassium sorbate had no impact on the ELISA titers of GP40. What does it learn us? Well, of course, that you can add potassium sorbate to colostrum. It will have, even if you use our vaccine, so bovilis cryptium, it will have no negative or whatever effect on the titers of GP40 antibodies in colostrum. So that's also what is written here. The time has no significant influence. Also the storage conditions, so room temperature of 4 degrees, had no influence. And the addition of potassium sorbate had no negative impact as well on the GP40 concentration. Another finding, and well, just to illustrate how potassium sorbate may work, and that it is a good preservative for colostrum. So we found out, and don't try to read it, but you see the red color. We found that 5 of the 18 samples that were stored at room temperature became solid. So there was definitely bacterial growth on those samples. And 4 of those 5 samples did not contain potassium sorbate. So again, that illustrates that you can use potassium sorbate as a nice conservative for bovine colostrum. So just some things to remember. I explained the vaccine, so it's a Rotavac with a different antigen. But it's good to give more colostrum. You saw the cycle of Cryptosporidium parvum. It's an intracellular parasite, which is, let's say, in the introcytes, but it's on the apex or on the top of the parasite, mainly, let's say, a bit external. So it's well hidden in the microbiome of the gut, and so it's difficult to reach. And that's what we also saw if you have vaccinated colostrum and you give it over 5 days, even mixed with milk replacer or with normal milk, it gives a better effect, a better protection. And we looked at a lot of trials also presented here today, and even at the same moment as I'm presenting now, that if you give 5 days of colostrum and transition milk, it has a beneficial effect on, let's say, the local immunity, the development of intestinal villi, but also on the microbiome and many other things, even the growth and other elements on the health of a young animal. What's also interesting, if you give longer colostrum or transition milk over 5 days, it's a way also to reduce what we saw, antimicrobial use. We see there's a lot of antimicrobial use in young animals. One reason may be Cryptosporidium parvum to prevent or to treat, but with the colostrum from vaccinated dams with this vaccine, you may also reduce the oocyst shedding, but also clinical signs as diarrhea by using a natural ingredient called colostrum. So it really helps you to manage Cryptosporidium parvum in farms without using antibiotics. Some other recommendation, well, in the fridge, we say now colostrum. You can keep it for, let's say, 3 days, and then it becomes, let's say, a contaminated soup. So that's maybe why you could add also potassium sorbate. In the freezer, well, you can keep it definitely longer than 3 days, maybe a few months, 6 months until 6 months. But then, of course, you need to thaw it, and then maybe a little hassle, of course, in your farm to add, let's say, frozen colostrum to milk replacer or even transition milk. Again, potassium sorbate, it gives many opportunities. It's something which is globally not really known in let's say, bovine medicine, but I think it's definitely something that can help you, and also in certain farms it can improve and also facilitate colostrum management. It's a different way to talk to your farmers and also to find solutions. So with that, I would like to thank you for your attention. I'm happy to take a few questions, and if you want to read shortly what I've presented, you can scan this QR code. Thank you.
Thank you very much, Dr. Geert. Is there a question? I would have a question.
Great.
I guess you've tried to assess the effect on the transmission of passive immunity within the cows, right? So I believe there's no effect. So it actually, the transmission of immunity is achieved properly, even with the inclusion of the potassium.
Yes, so well, we only did what we have showed here. So we did it in vitro, let's say, but we did not look at the efficacy of the vaccine if we would have put potassium sorbate through the colostrum. All the trials we have done so far with this vaccine were done with frozen colostrum that have been thawed, or fresh colostrum, or calves suckling their own dam in beef conditions.
Because right now there's no serum like assessment in cup.
Yes, exactly.
Okay.
Yeah.
Thank you. Any other questions? So thank you very much for your conference. And we'll be receiving right now Dr. Luis Arango de la Pava. He will talking about pharmacodynamic interactions in Artemisia cinia ethyl acetate extract, anthelmintic effect on Haemonchus contortus eggs and infective larvae. Welcome.
Thanks, everybody. Hello. I want to thanks to the organization to let me be here sharing my investigation results. I'm going to talk about pharmacodynamic interactions in Artemisia cinia ethyl acetate extract. Anthelmintic effects on Haemonchus contortus eggs and infective larvae. So Haemonchus contortus is the most pathogenic gastrointestinal nematode that infects grazing sheep and goats. It is characterized for being hematophagous, prolific, and resistant. And its clinical signs of infection are pale mucous membranes, low body condition, and diarrhea, which are not a solution. It can cause the death of young animals or can cause economical losses. Haemonchus contortus life cycle is divided into phases. Non-parasitic phases that starts when the animal defecates infected phases with eggs. The eggs start to develop to get until L3 larva, and then the parasitic phase starts when the animal, the larva gets into the animal while grazing. So the CO2 or carbon dioxide levels, the enzymatic conditions, and the pH remove the cover of the larva and develop to L4 and L5, that is hematophagous, then adult, and that lay eggs, so the cycle is closed. Traditionally, Haemonchus contortus treatment is traditional anthelmintics, but the inappropriate use of them leads to anthelmintic resistance. So it's necessary to look for another control solutions like the herbology. The herbology can be a source of new bioactive molecules that can be an alternative treatments. We propose Artemisia cinia as model of study and source of bioactive molecules. This is a plant that belongs to the Asteraceae family. It biosynthesizes different secondary metabolites, terpenes as artemisinin, flavonoids as pectolinarginine, and lignans as isoycine. These secondary metabolites are the responsible of the biological and pharmacological activity of the plant. Its traditional applications are for respiratory disease, inflammation, and dewormer. Its distribution is native from Central Asia, but now there's some greenhouses that cultivate this plant here in Mexico. There is some reports for the pharmacological activity of the plant. Regarding to its anthelmintic activity is report against Ascaris, Moniesa, and Haemonchus antelador-sarja from different extracts, principal aqueous and NA-hexane. Different reports for our research group have determined that the best extract to develop a future pharmaceutical preparation is the ethyl acetate extract, because it had a good activity against eggs and against larvae. Also have a very good yield percentage of extraction, so we are this work we are going to explain the separation and all these things of the ethyl acetate extract. Vegetal extract is a very complex matrix of secondary metabolites and bioactive molecules that can be act together in the same therapeutical target or different therapeutical target, leading to pharmacological interactions. A pharmacological interaction is the modification of the effect of a drug or bioactive molecule by the action of another when administered together. The effect can be increased or can be decreased. In this case, the pharmacodynamic interactions can be pharmacokinetic or can be pharmacodynamic. We're going to talk only about pharmacodynamic. That involves the modification of the response of the drug or bioactive molecule. If two bioactive molecules are mixed together and the result effects is the sum of both, it's an additive effect, and is more or is increased is synergism, or is less or is decreased, we talk about subadditivity. So we know that Haemonchus contortus is one of the most pathogenic gastrointestinal nematodes that affect grazing ruminant, especially sheep and goats, and generates a lot of economic losses due to the anthelmintic resistance. So we are proposing herbology as an alternative. So in this case, we propose Artemisia sina that produce different secondary metabolites as terpene and phenolic compounds, but it's necessary to determine its anthelmintic activity and the pharmacodynamic interaction that can have between them in order to, in the future, propose Artemisia sina plant-based pharmaceutical preparations with anthelmintic activity. So the main objective of this work is to determine the influence of pharmacodynamic interaction between the major chemical compounds of Artemisia sina ethyl acetate extract with anthelmintic effects on eggs and larvae. We have three different objectives: the isolation and the identification of the main chemical compounds, the determination of the leader compounds that is going to help us to perform the binary mixtures, and establish the presence of pharmacodynamic interactions in binary mixtures through isobolograms. This is the experimental diagram. We're going to use ethyl acetate to extract and purify the compounds. Then the compounds, we're going to determine the lethal concentration 50 and 90. And according to this activity, we're going to set as a leader compound. With the leader compound established, we are going to look for the presence of pharmacodynamic interactions in the binary mixtures through isobolograms. So this is the methodology for the first objective. We used pre-flowering plants that was collected from a greenhouse. The extraction was used through maceration. The result extract was separated in open column chromatography, using a normal phase as a stationary and a mobile phase with hexane and ethyl acetate. The stain was steric sulfate. All the separation were monitored through thin layer chromatography, and the samples were grouped according to its chemical profile. We get 48 different samples that were grouped in 25 different fractions according to its chemical profile. We isolate 3 different compounds. It was crystallized. C1R5 don't have any UV light absorption, and the other 2, yes, it have. This is a fuchsia stain that is characteristic of terpenes. So we think that these 2 compounds can be terpenes. So C1R5 was analyzed through gas chromatography. These 2 through HPLC, and the structural elucidation was through NMR. This is the results for the C1R5. There was a mixture with 4 different compounds, but 2 was the major. The quantity of this bot was like 70% of the mixture. One of them have a molecular ion of 124, the other one 136. According to NMR spectra, we have a primary alkyl group, and according to DTTQ, there's any CH signal. So there don't have any branch and was lineal molecules. So all the CH2 signals corresponds to the backbone of a structure. This is the proportion of structure of this first to C1R5 and 3 aconton and 1 non-acosanol. For the other one, for C113, this is the HPLC analysis. There's apparently a pure compound. This is the UV spectra that is characteristic of terpenes. And in the TPQ, we have 15 signals. It means that this has a terpene. We analyze all the spectral data. We compare with the literature, and we found that the first, this compound is called perubin. For the other one, have a similar UV spectra, also 15 different signals, but we suspect that the lactone group, that is this one, was open, so we perform an HMBC analysis that looks for the correlationship between carbon and nitrogens. We look for carbon-12 and the correlationship between H8 and H7. That is this one and this one. And we see that carbon-12 with H8 doesn't have any correlationship. It means that the ring is open. We look for the spectral data in the literature. We doesn't find anything. So this is a new compound that we are reporting, and we name it cynic acid. Then for the in vitro assays, we use a sensitive strain of Haemonchus contortus to ivermectin. We use approx 100 larvae and 100 eggs per well. The different concentrations, ivermectin as a positive control, and we follow the methodology reported by Coles and Van Wyk. The lethal concentration 50 and 90 were determined through probit analysis. These are the results. We can see that all the compounds have activity. Only cynic acid doesn't have activity against eggs, but all the activity report are higher than the ethyl acetate extract and is much higher than the therapeutic dose of ivermectin, that is 5 milligrams per milliliter. The possible mechanism of action of C1R5 is the interaction with phospholipids of cellular membrane affecting membrane fluidity and functionality. And the possible mechanism of action of the sesquiterpenes is the presence of alpha-methylene gamma-lactone system that acts as mycoreceptor, allowing the interaction with thiol groups of proteins. According to the activity, this one was the best in eggs, following one perubin. C1R5 doesn't have any difference with the extract in lethal concentration 80. Cynic acid was the most active, following by perubin. But taking into account the activity in both eggs and larvae and the purity, we select perubin as leader compound to perform binary mixtures. Binary mixtures was carried out using subsequent dilutions of lethal concentration 50 of leader compounds and isolated compounds in a fixed proposed scheme. And the excitation inhibition were performed through this methodology report. So we have the isobologram and the table. It means the same. So we have here the concentration of C1R5, the concentration of perubin, and we have here the line of additivity. All the points above the line of additivity means subadditivity, over the line means additivity, and below the line means synergisms. In the table, we have perubin, 100 perubin percent, and 100% C1R5, and the subsequent dilutions of the lethal concentration 50. This is the expected larval activity and the observed larval activity, and the relation between them is the ratio. Ratio close to 1 means additivity, higher than 1 means synergisms, and below or less than 1 means subadditivity. So we have synergisms in these binary mixtures against larval lethality. 4.8 times more active and 1.7 more active than expected. We suppose that this is because the different mechanisms of action of the different compounds are working together in different therapeutical targets. In the case of the perubin and cynic acid mixture, we see 1 point below it. It means synergisms. We can think that this is subadditivity, is this point, but is inside the standard deviation, so is additivity. This was in larva, and this is in eggs. Only we can perform the binary mixtures using perubin and C1R5 because cynic acid didn't present effect on eggs. We can see in these binary mixtures that only present additivity in all concentrations. So in conclusions, we identify 4 different compounds in artemisia cinetyl acetate. The binary mixtures were established using perubin as leader compound and was found synergy between the perubin and triacontanol and 1-nonacosanol mixtures that was 4.87-fold more active, and perubin cynic acid that were 1.42-fold more active in lethal effect in L3 larva of Haemonchus contortus. And thanks for the leader of the group of investigations and our collaborators, and thanks.
Thank you very much, David Arango. Is there any questions that you would like to ask regarding this synergistic activity of phytochemicals? Thank you very much. So let's move forward. We'll welcome back Dr. Damien Achard with the efficacy of an oral solution of paranomizin for the treatment of suckling beef calves with cryptosporidiosis in a multicentric field study. Thank you, Doctor.
Thank you again. Thank you for the scientific committee for the invitation. I first have good news for you. I'm the only thing standing between you and the lunch. So when my presentation is done, after it's lunch for everyone. Okay. I will not speak too much of this introductory slide because I think many things has already been done at the beginning of this session regarding cryptosporidiosis by Dr. Ortega-Mora. And I think I will jump to the 3 elements that, in my perspective, make cryptosporidiosis particularly difficult. The first point is related to the oocyst, which is the form of resistance of the parasite in the environment. And we have seen this morning how robust this element was and resistant in the environment, as well as the low dose of infectivity required to induce clinical signs in neonatal calf. The second point, and was mentioned this morning as well by Dr. Ortega, was in the cycle of a parasite, there is this auto-infection phase, which is important because it actually amplifies and accelerates the disease, and it leads to inevitably a high burden of oocyst in the farm environment. And the third point, which makes this disease particularly challenging, as you know, is that we don't have so much tools in our hand to try to control, prevent, and treat. And to end this session, I will focus on the treatment part, meaning the treatment addressing the treatment of sick calf. So let's talk a little bit about paromomycin. paromomycin is an antibiotic from the aminoglycoside family, as you know, with broad spectrum activity. It's been used since 15, 20 years plus to address cryptosporidiosis. And although we have nice evidence of its efficacy in calf, there are some gaps that remain to be addressed. And one of them is actually the field efficacy on a large set of animals in beef suckling calf. Until now, we have not any published evidence of efficacy of paromomycin to address this in beef suckling animals. And looking at the epidemiology and the prevalence of cryptosporidiosis, at least from a European perspective, we can clearly see that the issue is as dramatic as it is in the dairy herds that we have in Europe. So we have in Europe more than 10 million of calf, beef suckling calf. We know for a fact that crypto is present in mainly every herd with approximately a 12 to 30% presence in calf feces. So this study here was determined during the registration process of the product we have in SIVA, which is gabapentin multi oral solution to address cryptosporidiosis, and we compare it with the positive comparator at that time, which has a claim for the treatment, which is allofuginol. So it's important to frame it. So the population of calf that we are considering are obviously beef suckling calf, and they are clinically ill, meaning diarrhea, with cryptosporidiosis only. That means that they were negative for rota, corona, and they have to be positive, of course, for cryptosporidiosis parvum and diarrheic as well. You see the age of the animals, so it's 3 to 14 days age animals, so really representative of what we see in the field, natural infection, no use of allocure preventively, and calf were randomly segregated into two groups. So calf from group A received paromomycin 150 milligram kg in one oral dose per day for 5 days, and the animals in group B received allofuginol once a day for 7 days. And the study duration was planned to be 21 days, but we hit the COVID-19 situation, unfortunately. The parameters that we have followed were very classical, so clinical endpoints, fecal score from 0 to 3, so a score, just to be clear, a score of 2 or 3 qualify as diarrhea for calves. We follow, of course, general health observation on the same type of scoring, hydration score as well, so on a daily basis. And on a parasitological aspect, we have followed quantitatively and qualitatively the oocyst excretion by a basis of a strip and basis also of immunofluorescence technique for the quantitative aspect. And we also intended initially to measure the body weight, initial body weight and the terminal body weight of the animals. The outcomes that were decided were there was a primary outcome which was clinical cure. So clinical cure here in this study is an aggregation of a clinical cure at day 7 and day 8. So the animal had to be clinically healthy for two consecutive observations. And you see that the thresholds are pretty conservative. So the animal need to have no diarrhea, a perfect general health status, and a perfect hydration score. You see other parameters that we decided also to follow during this regulatory study, the time to first clinical cure, so in a very survival curve way, the number of days when calf were not expressing diarrhea, the parasitological cure, and the mean daily body weight gain. And finally, of course, we document every safety issue that could have occurred during the study. In terms of statistics, so the statistical unit here was the calf. We intended initially to run a non-inferior trial in comparison to Allocure, and we expected both treatment to give approximately a 70% clinical cure. And based on that and a power of 80%, that's the number of animals in each group that we would need, 147, in order to reach this target. So let's dig into the results. So you have here the geography and the location of the different farms where we conducted this regulatory trial. A majority of these farms were in France, so 35 commercial beef suckling herds in France. 5 extra were also recruited in Belgium. And all those calves, they have a recent history of cryptosporidiosis for sure. So in the end, 191 suckling beef calf with cryptosporidiosis diarrhea could be involved in this study. A majority of them, by a narrow margin, were female. The median age of inclusion 7 days, so in line with what we see in the field. You see that, yeah, as usual with beef calf, there is considerable variation in their body weight, from 28 to 86 kilo here. And then we could divide the calf equally into the 2 treatment group. Unfortunately, the study, and we didn't plan it as you can imagine, but we had to terminate the study because COVID-19 basically was here and Europe just shut down everything. The good thing for us is that all the data from day 0 to day 8 was acquired on all the calves, so all the first part of the clinical benefits associated to the intervention could be measured, but the terminal aspect of it, and mainly the body weight, which was evaluated at the end, could not be acquired, unfortunately. So at baseline, so what you are looking here is the, I would say, clinical parameter and the parasitological parameter just at the start of diarrheic episodes and the initiation of the treatment in both groups. So group A, which is labeled as a dark blue bar, and I would say group B treated animal, which is labeled here in a light blue bar. What is evident from this is that at baseline, those calves in both groups are equally sick from cryptosporidiosis. You can see and appreciate that on the fecal score graph, on the general health score, GH score, as well as the hydration score. In terms of oocyst, those calves excreted in both groups around 4 million OPG per gram of feces in both groups. First result, that's the pivotal primary outcome, and this is the clinical cure obtained at day 8. So I remind you that it's the calf has to be cured for day 7 and day 8 to qualify as being really cured. And we reached 91.5% in group A and 68.1% in group B. It turned out it was above non-inferior, so it turned out that it's statistically superior. And when you adjust this differences between the two groups, adjustment based on age of the calf, the clinical score at the day 0, and the breed, the probability to be cured was 35% higher in animal receiving the treatment in group A. You have here more details about when the calf could be cured. So on the top here, everybody is sick. So every calf is sick. And then by the end of a study, of course, what you want to see by a treatment effect is that the animal get cured. What is evident is that the animal that received the treatment in group A show, starting at day 3, a faster cure than the animal that received the treatment in group B. And the quantitative aspect of it is that when you do the stat, there is 48% higher probability of being cured in group A at any time compared to group B. And that inevitably translates into a benefit in the numbers of days when calves don't have any clinical signs, don't have any diarrhea, and it's an immediate benefit of 2 days without any symptoms and signs of disease. In terms of parasitological cure, which is the other aspect of control of Cryptosporidiosis that is really important, you see that there is also a difference between the two groups. Animal receiving the treatment in group A had 79.3% of parasitological cure at day 7 compared to 63.7% in group B, and this was statistically significant. The same, so looking at the oocyte excretion in a different way, expressed a little bit differently here as percentage of positive samples, and you see again the same labeling, so animal in group A with a dark blue and animal in group B with a light blue, and there is the higher, I would say, percentage of calf that get lower percentage of positive sample and a better parasitological cure with animal in group A, and it's statistically significant at day 5 and day 7. Other results, so as I mentioned at the beginning of my talk, we had to terminate the study before day 21 due to COVID-19 outbreak, so this analysis could not be performed. In terms of safety, we observed no adverse event that could be possibly related to the effect of treatment in group A. Conversely, we observed 2 serious adverse events with digestive clinical signs in animals from group B that were assessed as possibly or probably related to the treatment. So, in conclusion, although simple, this study, I think, is important because it's a landmark study that documents the performance of paromycin orally distributed to beef suckling calf. One challenge that we had during this study for sure was COVID-19 situation. I can tell you it was pretty difficult to handle, but very proud to have been able to finish it and to present it to the legal authorities. And it's a confirmation of the potency of paromomycin to address cryptosporidiosis in diarrheic calf when used at the right dose, 150 milligram per kg once a day for 5 days. If you wish to know more about the dose of paromomycin that is beneficial, or if you would like to know a little bit more about the impact of paromomycin on the commensal flora, I would be very happy answer your question through the poster session tomorrow morning. Thank you very much.
Thank you very much, Dr. Achard. So to finish this block, are there any questions regarding the subject? We are...
Oh.
Go, please.
Is this Peter? I will have a good question then.
Okay, thank you. Peter Constable, University of Illinois. This is more of a comment than a question, but congratulations on doing a study with appropriate endpoints. We published a study in 2013, and I have never found a paper published before that study as to the duration of diarrhea that calves have. A very fundamental question. Nobody measured that up until 2013, and it's still been very rarely measured. So for the students in the audience right here, read the literature, and there's a lot that we should be measuring that we actually haven't. So very excited to see clear evidence of efficacy right here. So thank you and congratulations.
Thank you very much.
Thank you very much, Dr. Constable.
Any other questions, comments? No, we are way too hypoglycemic right now. So let's go to a lunch break for 2 hours. We thank you very much, Dr. Achard. And we'll be seeing you at 15:30 for the symposium, which is sponsored by MSD. So see you in about 2 hours and good appetite.